if you compute now the inner product with an arbitrary mode operator and this conformally soft primary, you will see that you land on the soft photon charge that that was computed in well, that were shown to, whose insertion was shown to be equivalent to the soft photon theorem. For a spin 2 case, a similar story happens, but actually it's more puzzling here. Because now in the conformally soft limit delta equal 1, because J is 2 and delta equal 1, you will land on an object that has a weight nh h bar, which is equal to 3/2 and -1/2. Expand this guy or near scry, you can read that this object corresponds to the Goldstone mode of super-translation symmetry on the celestial sphere, where the super-translation parameter takes this form. Again, the inner product involved in this mode gives you precisely the soft photon charge at scry plus. So interestingly, the descendant of this mode, so you can associate it to this inner product a sort of 3/2 minus 1/2 object, and its descendant, so its derivative, give rise to an operator which was called the super-translation current, and who satisfy the following OPE on the celestial sphere. So the funny aspect of this mode is that it shifts the weight by 1 unit. So this is a property that is probably not so familiar in usual CFT. This is why the super-translation symmetry are actually pretty original compared to the usual thing that we know in CFT. So now we can naturally turn on to a super rotation. So what happened for super rotation before mentioning the celestial story? Let me remind you that the original proposal for super rotations were given by Glenn and Cedric in their paper. So it consists of considering local conformal killing vector on the sphere. And Strominger and collaborator have shown that because of this relationship between asymptotic symmetry and wide identities, wide identity of symmetries and soft theorem, they could infer from the existence of Virasoro symmetry a new theorem, which they call a subleading subgraviton theorem. So it's a subleading in the sense that it's subleading in the energy expansion. So the leading subgraviton theorems goes like 1 over omega, and the subleading subgraviton theorem goes like omega to the power 0. And this thing is actually precisely projecting out the 1 over omega divergence. So they show that this theorem implies the Virasoro wide identity for the CKV kind of meromorphic superrotation. Now, these relations were not found to be bijective, namely, it was not shown that this wide identity implied the subgraviton theorem. To do this, Campiglia and Lada proposed that superrotation should be extended to include the full diffs2 on the sphere. And in that case, they could show one-to-one correspondence with the soft theorems, but this required an enlarged phase space. So we will see that in the celestial picture, these two proposals can be related in the following way. So what was going on for this case is that for delta equals 0 and the shadow primary where delta tilde equals 2 are two modes reduced to pure diffeomorphisms. And this is what we call Goldstone modes. So this is the shadow primary with delta tilde equals 2, and is the shadow of this primary with delta equals 0.
So you have 5 more minutes.
Yes, thanks. So you can actually see that these pure diffeomorphisms are exactly the super rotation. Now you just need to remember that we are in a different gauge. We're not in boundary gauge, but in harmonic gauge. So the important thing to notice, I'm skipping a few things here, is that you can realize that this mode corresponds to a Virasoro or super rotation kind of symmetry, because it violates the CKV, the conformal killing vector equation at isolated points. So it introduces a singularity on the celestial sphere, gamma AB, at isolated point. On the other hand, the delta equals 0 primary correspond to the full to Diffes 2 symmetry because it modifies the celestial sphere metric. Now we computed the symplectic structure involving this mode. So notice that this required renormalization procedure that was developed by Geoffrey, Adrien, Romain. And when you compute this symplectic structure, you land on the soft part of the charge, but now where yz is an arbitrary function of z and z bar. And when plugging the shadow primary, you directly land on what was called the 2D stress tensor for the gravity that was found by Capek, Mitra-Aquilariu, and Strominger. Why this was called like that? Because insertion of the stress tensor in a scattering amplitude obeys the wide identity of a 2D stress tensor. Now the other mode, the other Goldstone mode where delta equals 0, it gives us what we have called the shadow stress tensor, which is, this is precisely actually the shadow operation in 2 dimensions of a 2D stress tensor. And it has weight -1, 1. So in summary, the shadow transformation commute with the normalization procedure. And the main point I want to make here is that the super rotation, the Virasoro super rotation, and the Diffes 2 are on equal footing via this shadow transform. So in other words, one can indeed go from the Virasoro wide identity to the subleading subtheorem by allowing the asymptotic symmetry group of Einstein gravity to be closed under the shadow transform. So let me finish here by saying that we have studied conformal primary wave function in celestial holography, where the labels are spin and a conformal dimension. We have looked at the so-called conformally soft mode, which arrive for several limits of the conformal dimensions. And we have shown the relationship between asymptotic symmetries and different proposals for super rotation symmetry. Now I want to say that the property of celestial CFT, as Andrea mentioned, are just starting to be understood. And there are many, many things we can keep exploring. For instance, the existence of a sub-leading and sub-subleading subtheorems are something we are looking at right now. So thank you very much.
Thank you. So, well, thank you for keeping the time and for this very interesting talk. So we have time for questions. So if you have a question, please raise your hand. Ali? So I will.
Yes. Thank you for the nice talk, Laura. So my question is that if you go back to the very first slides where you showed the...
I stopped the share because I cannot see you, but
okay,
yeah, let me put it, yeah.
Yeah,
the very first slide.
No, maybe
this?
Next one. No, well, you show, yes, this one.
This
yeah,
one?
so this, yeah, with the diagram. Yeah, so this picture is a bit, might be misleading because we might assume that this is like a localized particle that is going to null-infinity, but somehow, if I understood correctly, you're talking about plane waves that are propagating in that direction. So my question is that Now, if you consider a localized wave packet and do this Mellin transform, what do you get?
I'm not quite sure I understand what do you mean.
So yeah, this so you show the transformation from
Yeah, from the plane wave here.
plane wave, yes, here. So this is really a plane wave, not a like a point like particle. So if you want to do that, you should consider that like a localized Gaussian wave packet, for example.
Okay.
And then, well, we can do this Mellin transform. But my question is, for example, a wave packet that propagates on, let's say, retarded time u1, what is the difference between that and another one which propagates at time retarded time u2? So how do you see it in the Mellin transformed version?
Well, I guess you would do a Fourier transform to change your time to the mega, and then you would Mellin this quantity.
Yeah, I mean, in the final the information that you have at the end, you have the z's, which is not changed because it's just the same direction. You have the spin and the weight. So
yeah, the weight.
this,
I guess it would be the weight.
the weight will be changed.
I suppose, yeah.
Thank you.
Okay, so Laurent is next.
Hello, Laurent. I have a question. It's a technical question because you went fast in one of your last slides when you were the generators of symmetry. It looks like the generator of symmetry for DFO is a local integral on the sphere, but it looked like the generator of symmetry for the dual transformations is an integral that is U dependent, right, over all sky.
Right. This is always a feature of the soft charge. So what people sometimes call the flux, or it's you go from the collimation to integral, and then you integrate over U. You use the constraint, and then you get this.
The sphere. What's interesting is that the sphere you don't need to do that. The sphere is directly, and if I understand properly, the second.
Right. Yeah.
It's directly defined as the corner.
That would be your corner.
Yeah.
Your corner charges. Yeah.
That explains why in the covariant phase space formalism it's maybe easier to access this one, whereas the one associated with the the dual transformation are so far nobody knows how to access them.
Right. You mean the time development of your corner?
Well, I mean, yeah. We know how to generate the generator of D phase 2 asymptotically after renormalization, but so far not the conformal generators.
Okay.
But okay. There's no log. Yeah. Anyway, that was the question. Thanks.
Okay. 2 other quick questions. Yannick is next.
Yes. Yeah. Yes. Thank you for this nice talk. I have a naive question. So, is there any known relationship between these scattering amplitudes written on the celestial sphere with the CHY formulas, where people write scattering amplitudes in terms of these scattering equations? And if I remember well, there are spheres appears as well.
Yeah, I think there are some papers. I mean, maybe Andrea knows better the reference than me, but I think there has been some.
There was a paper last week by Eduardo Casali and Atul Sharma that discusses in particular how the celestial double copy arises from the Asymptotic worksheet, and they write down the celestial CHY equations.
Mm-hmm. Thanks.
Okay, last question, Luca.
Yes, hi, Laura, thanks for the talk. Very quick, or at least I'll try to. So we said that super translations, they change the conformal dimension, they shift it +1, right? At a certain point of your slide, you said that the super translation operator. Now, the question that I have is, first, is that true also for translations, so angle independent transformations? Or that would not change the conformal dimension?
I don't think they will.
Okay, so that's really a feature of the angle dependency of the transformation.
So, yeah.
And the second question that I have is it the +1 over there is just something that you impose, or you can get something like +2 eventually if I do something different?
No, for this this given operator current, you really compute the OP, which is just, you know, you can start from the wired identity and you will get omega here over in the usual plane wave base is omega divided by z minus w. You Mellin transform the left and right, and you see that this is just shifting delta by 1 because you have omega times omega 1 minus delta, so it's like shifting delta by 1.
Okay, I see. Okay, thanks.
Okay, there is no other question, so let's thank Laura again.
Thanks.
And then we move to the next talk by Angelos Fotopoulos, Celestial CFT and Extended Super-BMS Algebra.
Yeah. I can share now the screen.
Yeah, you can share the screen.
Thank you very much.
Normally.
Yeah. Okay, I'm going to go to my talk now. Let's see that everything works fine.
Looks like we see your screen. Yeah.
Now we can see it?
Yeah, we can see it.
Okay, perfect. Thank you very much. So I would like to keep the time of my talk to the 50 minutes that it is. Thank you very much for the kind invitation and for this very interesting workshop. The title of my talk will be to discuss celestial CFT and the extended super-BMS algebra. So I see I did not start my video. Excuse me for that. So the work that I will be discussing is based on work that I've done with collaborators Wei Fan, Thomas Taylor, Stefan Stieberger, and Bing Chu in the past few years. The basic idea. Our basic idea starts like that. In 4 dimensions, we have amplitudes, which involve transitions between momentum eigenstates. These are the typical plane waves. We compute these things by computing basically Feynman diagrams. Okay, and Lorentz invariance and translation symmetry that are manifest in this picture. Now, we will see that there is a map that allows you to go from the standard 4-dimensional amplitudes to expressions that describe correlators of conformal primaries in a 2-dimensional conformal field theory. This mapping involves that we start from energies here, and energies are being transformed basically into conformal dimensions of primary operators. Moreover, the direction where the momenta point towards the asymptotic boundary of flat space-time, this momenta direction, they are mapped into positions on the celestial sphere where we localize these operators. The Lorentz symmetry in the left-hand side in this picture is mapped into global conformal symmetry on the celestial sphere. So this is a very interesting picture, and this would be basically my main motivation. So let's see why I would like to study this guy, what I will call celestial CFT. The first question is the asymptotic symmetries, okay? As was discussed already by several of our speakers and Laura also before me, there's been a lot of developments in the past few years that demonstrate that asymptotically flat space-time possesses many more symmetries than the naive Poincare symmetry. There has always been a revived interest in the soft theorems of 4-dimensional quantum field theory. There's been various attempts to use these soft theorems and locality to completely fix the S matrix of some theories. We will see that actually asymptotic symmetries constrain scattering amplitudes, and vice versa, that would be the interesting thing, the underlying celestial conformal field theory should be able to allow us to construct them from first principles. So we should be going back and forth between celestial CFT and amplitudes. That's actually one very interesting motivation for studying this theory. But I would say probably the main motivation of mine and quite a few researchers is flat space-time holography. Usual holography describes gravity in a bulk space-time, and it's turns out that it's dual to some conformal field theory on the boundary. But here the interesting thing is that we are discussing flat space-time holography. So we will be discussing gravity in flat space-time, and we have a dual description in terms of conformal field theory. Finally, there's been several connections in the last few years that show that gravity amplitudes, the gravity S matrix, can be written as a double copy of gauge theory interactions. And these have appeared in string theory as KLT relations. Recently, we have the double copy construction. The interesting thing is that conformal field theories in 2 dimensions, like the celestial sphere, they have similar constructions that appear when we have an extended symmetry beyond the Virasoro symmetry, which is the Kac-Moody symmetry. So all these ideas that kind of motivate us to say, okay, well, might be interesting to study the celestial CFT. So, one second, sorry about that. The outline of this talk. And as I said, I will try to keep some time about that. I will discuss the celestial CFT basics, which we already had one very nice talk by Laura and one earlier by Andrea that unfortunately was unable to attend. I will discuss conformal primary wave functions, celestial CFT operators, Bellin amplitudes, and relation of those two correlators on the celestial CFT. Then I will try to explain how we can extract the operator product expansion in celestial CFT from the S matrix. The next step will be to understand the symmetries of the celestial CFT and the relation to soft theorems of the typical soft energy theorems that we know from Weinberg and recently by Strominger and Casaro. And eventually, from this construction here, we will try to find out what is the symmetry on the celestial CFT, and it will turn out to be an extended BMS symmetry that was discussed by Barnett and Trossard in the past few years. The next part of my talk, the last part, will be a supersymmetric extension of the previous ideas. So it will go a bit faster in the sense that once we understand these things, then it's, of course, technical, but a bit more straightforward to find out supermatrix of conformal primary wave functions and the relation to celestial CFT operators. We will be discussing OPs of fermionic fields, fermionics of theorems, and eventually we will try to take OPs of super-BMS fields and extract from those the super-BMS algebra. So the basic idea as we have it in our mind. In momentum space, we have plane waves with some momentum P, which we can parameterize by the energy omega, and some null vector Q that tells you which direction the momentum is pointing. In conformal basis, if we want to study celestial CFT, we would like to have some conformal primary wave functions. And I will be a bit redundant here. I'm not going to put all the symbols. I'm going to discuss a conformal primary wave function like this one. And the important thing about those is that they should have nice properties. They should transform nicely under global conformal transformations, under SL2C. So in principle, we expect to have some kind of field, some wave function, that under an SL2C transformation transforms in this manner, with holomorphic weight h, and at the holomorphic weight h bar. And as already was discussed earlier, the sum of the two of them corresponds to the dimension of this conformal primary wave function, while the difference corresponds to the spin. Now, holography tells us that to each conformal primary wave function like this one, we should be able to associate a conformal field theory operator with the same conformal weights as the conformal primary wave function. So that would be our holographic picture. So how do we do it? How do we go from massless particles to actually describing them in terms of conformal primary wave functions, and then, of course, dually to operators on the CFT? The idea is that we start with this parameterization of the energy. I'm sorry, the four momenta in terms of energy and the null vector. The null vector is parameterized by these coordinates z and z bar, which actually would correspond to the positions on the celestial sphere where the particle enters or exits. So in the massless case that I'm primarily interested, the transition from momentum space to the conformal primary wave functions implemented by the Mellin transform. Here I show the Mellin transform for very schematically, but basically what it does is to take you from a wave function momentum space that depends generally on energy, the helicity, and this z and z bar which parameterize the null momentum, and it takes you to a new function that depends on a conformal dimension delta and the spin j, which actually associated with the helicity. Moreover, it turns out that the dimensions they need to belong in the principal continuous series, as it's called, if we want these operators here, these conformal primary wave functions, to be orthonormal. So these guys will be described by a point z bar on the celestial sphere, where the massless particle enters or exits, and the SL2C waits. So, an example, scalar field described by a plane wave. You can make a Mellin transform and you arrive to this expression. This expression, you can check that it transforms exactly with conformal weight delta under the SL2C, which is the global conformal group. And of course, this is a spin J wave function. It moreover definitely solves the Klein-Gordon equations. This is a superposition of plane waves. Okay. So this is just another wave packet. Instead of using plane waves, we use different wave packets that have nice properties. Now we go to our main interest, amplitudes. What we would like to do is to use the same picture to start from amplitudes that we construct using Feynman rules, which typically they depend on momenta and polarizations. We write these amplitudes in the spin or helicity notation, which makes manifest the energy factors and these coordinates Zi and Zj. So we parameterize basically the momenta, as in the previous picture, in terms of energies and a null vector. And in the spin or helicity notation, it's very simple to see that these amplitudes eventually will depend completely on these brackets between spinors. And then we employ the Mellin transform. And since the Mellin transform takes plane wave packets to conform our primary wave functions, we expect that the final result, which is a Mellin transform of each external state, you see this is the Mellin transform of each external state of this amplitude. This Mellin transform will have nice properties under the global conformal group, and holography tells us that we should associate it with a correlator of conformal primary operators. Which these conformal primary operators, they are the operators that live on the celestial CFT. So this is the basic idea. Starting from standard amplitudes in momentum basis, go to Mellin transform, and then holographically this corresponds to CFT correlators. Now, we would like to understand what we need to do in this picture. The first thing that one would like to do would be to study the operator product expansion. The operator product expansion in any CFT is a very important tool for constructing correlators. Okay, so let's see how this operator product expansion emerges in the situation that we're describing. How can we relate it to something that we can see in the four-dimensional gauge or gravity theory? In gauge theory, scattering matrix, there are particular limits which are called collinear limits, where two momenta of two external states, they become collinear. That means they travel in the same direction. And it turns out that in gauge theory and in gravity under some assumptions that I'll explain later, gauge theory amplitudes in general develop singularities. The very interesting development in the past few years is that these singularities, the collinear singularities, and soft theorems that are related to energetic, so basically constraints that come from the form of amplitudes under soft energetic particles, they can be run, it's a program that you can almost think that you can run backwards. So if you use constraints from here, you can fix the S matrix completely. Okay. So this is, let's say, the big dream of the S matrix problem. So you would like to understand now how this picture emerges in the celestial CFD. The very interesting thing of this parametrization that we use for the momenta, which we write in terms of energies and this null vector, is that when two momenta become collinear, this corresponds on the celestial CFD to two operators approaching each other on the celestial sphere. And what we know from conformal field theory is that when two operators approach each other, in generally, we can expand their product in terms of local operators with coefficients that in principle can be divergent. So basically, depending on the separation between the 2 points, these coefficients here can blow up. Particularly these divergent terms in the operator product expansion, as we call it in the CFD, are very important because usually these ones are the main ingredients for constructing correlators. These terms that are being omitted here are they're not singular. They correspond to extra terms that, for example, if we're discussing the OP between two primaries, then we expect it to give us another primary with a singular coefficient, and the extra terms omitted here, they correspond to what we call descendants of the primary. So this form of the singular terms is basically fixed completely, almost completely, by global conformal symmetry. Well, in 2 dimensions actually by Rarita-Schwinger symmetry. Okay. So what it turns out is that this form here is completely determined by the conformal weights of these two operators here and the conformal weight of this operator where the two of them fuse into. The let's say the only thing that you cannot fix based on symmetries is this structure constants here,Cijk. This tells you which fields fuse to give you which field. That's the idea. So the important thing now is that if we know the structure constants and we use Rarita-Schwinger symmetry, which is stronger actually than global conformal symmetry, we can fix completely the operator product expansion. So everything here that's being omitted. Okay. And at the end, we should be able to compute any conformal field theory correlator. So vice versa, you would like to think that if you understand this thing from the CFD point of view, maybe you can go backwards and understand similar things in terms of the space-time picture, particularly will be interested for gravity eventually. So how do we study these collinear singularities? How do we see them? A typical situation. Consider a scattering process. I'm considering Einstein-Yang-Mills theory here. And you consider a scattering that involves, let's say, gluons and gravitons. And imagine that two gluons are becoming collinear, or they're approaching to become collinear. Then there's a set of diagrams, a set of the Feynman diagrams, which actually is the most important because it can develop some kind of singularity. These Feynman diagrams correspond into diagrams that have this 3-point vertex right here, where you have two gluons and let's say an exchange graviton here. I use the gravitons as being exchanged between the two gluons and the remaining part of the amplitude. This is what is left. This amplitude here, this diagram actually here, can become singular, can develop a singularity. The singularity would appear because of the propagator of this graviton, which blows up in the collinear limit. Of course, I say it may be because we have also the 3-point vertex that depending on each form, it could give you some kind of cancellation. These two, this epsilon 1a and epsilon 2b, they correspond to the polarization vectors of the gluons. Okay, so this whole thing here, this SG nu nu, is called the splitting function. So this is basically the idea behind that is that if you look at the collinear limit of two gluons, let's say, the amplitude would factorize to a splitting factor, this guy here, times the remaining thing. Going into spin or helicity notation and looking, let's say, at this diagram here, which involves a graviton exchange, we can imagine it as two gluons fusing into a graviton, and then the amplitude factorizes to a factor like this one here, which is singular. Well, it depends actually on z over z bar in terms of the celestial sphere coordinates, but in a sense, if you consider this thing as being independent complex variables, there's a singularity. And you see that you have this factor here, and then instead of the two gluons, in the remaining amplitude, you have a graviton, either of helicity +2 or of helicity -2. Similar diagrams appear when two gluons become collinear and they exchange a gluon. So two gluons fuse into another gluon. You get singularities that are actually stronger. They go as 1 over z bar or 1 over z. And in particular, you can see also that these factors that involve the energy, they can become divergent if one of the energies becomes soft. We will see, and I will explain it also a bit later, that the leading soft singularities of amplitudes that are associated with the soft theorems, they come from the same diagrams that you have the collinear singularities. So there's no surprise that you get these poles here if assuming that the energy of one of the gluons becomes soft. Okay, so this is the complete picture, but it's very nice because it kind of hints you to exactly what you expect for operator product expansion. We said when the operator product expansion, we can imagine two operators approaching each other, fusing to a new operator, and basically this new operator would be, for example, in this case, a gluon operator of plus or minus helicity, or a graviton operator of +2 or -2 helicity. So this picture is very much looks like a singular factor times the remaining amplitude, and it kind of hints that, okay, this should be actually the celestial CFT-OP. And indeed, the only thing you need to do in this expression is to take the Mellon transform. And if you take the Mellon transform of the previous expression, this is equivalent to saying that two celestial CFT operators with spin -1 and spin +1, when they approach each other, they have an operator product expansion that can give you, by the way, these colors, these indices A and B and C are color indices and described with gluons. So they can fuse to another gluon operator, I'm going to call it, of spin -1 or +1 with singular terms like those here. Or they can fuse to a graviton operator, which has singularities of this type. These structure constants here turn out to be actually beta functions. So they're nice, simple expressions of the dimensions. Now, what we have shown basically is that we can start from collinear limits of four-dimensional Einstein-Yang-Mills amplitudes and get the operator product expansion of operators on the celestial CFT. The interesting thing that was done around the same time that we did that paper here is that you can go backwards. In other words, you could assume that you have an OPE between two celestial CFT operators like that without knowing the structure constants, just knowing that there are some singularities that you can deduce by dimensional reasons. Expecting that you have an Einstein-Yang-Mills, you can do some kind of analysis that tells you that what kind of singularities you expect here. And then the interesting thing is that you can apply BMS symmetry on both sides of this equation. And at the end of the day, you will find the form of these structure constants. It will be the same beta functions. So it seems that we kind of have like a nice picture that tells you that you can start from collinear limits of Einstein-Yang-Mills and you can get OPEs of the celestial CFT, or you might be able to start from OPEs of the celestial CFT and from first principles and consistent conditions get the structure constants, which of course should correspond to the collinear limits in the four-dimensional Einstein-Yang-Mills theory. So this extended, I call here BMS symmetry, we'll see what I mean by extended, seems to be very, very important because in standard CFTs, you can tell exactly what are the dimensions of the operators in the operator product expansion and what are the singularities you expect, but you cannot fix these structure constants. These are theory specific. They depend on each specific CFT you're considering. Here it seems like the symmetries of the theory might be able to fix completely this guy here. So I want to study the symmetries of the celestial CFT, and I'm going to just quote something that we already know, that a null-infinity we expect to find, of course, of asymptotically flat spacetimes. We expect to find Poincare symmetry, but it has been shown that you can actually find more symmetries, which were called the BMS symmetries. And this constrains the S matrix, and they provide non-trivial consistencies on amplitudes. So I would like to see what this thing can tell us about celestial CFT. So let's see first how we can see the standard symmetries. The first one we discussed was Lorentz symmetry. We learned that Lorentz symmetry corresponds to the global conformal symmetry on the celestial CFT. Indeed, you can take a Mealy amplitude, apply a global conformal transformation, and you find that it transforms covariantly with conformal weights h and h bar, which are written here in terms of dimensions and spin. And this is exactly what you expect. One thing that you probably don't see directly is translation invariance. So you ask, okay, how is this manifested in the celestial CFT? Well, you can take, for example, this combination of the momenta, which is called null momenta. And if you basically apply this operator on this type of expression here in the four-dimensional scattering amplitude, and then you apply Mellin transform, you find that this combination here in momentum space corresponds on the celestial CFT to an operator that shifts the conformal dimensions. In other words, applying this operator on a Mellin transform, which corresponds to correlators of conformal primaries, will result into shifting the dimensions of these operators. So this is what Poincare, what normal translations seem to do. Okay, you can do the same thing for other combinations. You will find shifts. Now we would like to see, though, we learned, and I already mentioned at the beginning, that we expect more symmetries on this. So how do we see these guys? We will try to use soft theorems. So in a usual quantum field theory, I will be this for case theory or gravity because it's not for any quantum field theory. There are some theorems which are called soft theorems, which are they tell you that when you take, let's say, gravity, you take a graviton to become energetically soft, the amplitude should factorize to an amplitude that involves the remaining particles, which we call hard, and some factors here, which are called soft factors. You see that the leading one, which was found some time ago by Weinberg, goes as 1 over the energy of the soft particle. And it has a factor here, which the important thing is that this factor is universal. Its structure is universal. It depends on polarization and momenta of the hard particles, as well as the momentum of the soft particle, the direction of the momentum of the soft particle. The energy has been factored out here. The interesting thing that was found by Cacciaso and Strominger, and by the way, in passing saying, this exact, actually, way to extract this soft behavior goes exactly the same way as the collinear limit. In other words, it is the same set of Feynman diagrams that contribute to this behavior, the same ones that I showed for the collinear singularities. The interesting thing is that if you continue and you expand to expand the energy to the next order, you find what we call subleading soft factors, which actually turn out also, the first subleading and the second subleading in gravity turn out to be universal. Universal means that they have the same structure, no matter what is the field content of this scattering process. Now, if you proceed and you do a Mellin transform of a scattering amplitude of n+1, let's say, gravitons, it turns out that you find poles at specific dimensions of the graviton operators. This is a manifestation on the celestial sphere of these soft theorems that appear in the soft energy limit. That was already discussed by Laura just before. So we find that a specific integer values of the dimensions, the Mellin amplitudes present some residues so they diverge. And we associate basically these divergences with what we call conformally soft theorems. So these operators that belong in these integer values are actually operators that are not in the principal continuous series. They're called conformally soft operators. And basically the idea is the same way that Strominger showed that soft theorems imply word identities for the BMS symmetries. Okay, we will try to show that conformally soft theorems lead to word identities for the symmetries on the celestial sphere. So, how do we find the word identities of the let's say conformally soft theorems? Okay, we will start first. We would like to find the energy momentum tensor of a celestial CFT, and the energy momentum tensor is supposed to be an operator that has dimension 2 and spin 2. Okay, now we have one particular situation in the Mellin transform. When a graviton becomes conformally soft with dimension 0, we find a pole in these Mellin amplitudes. So the question is, how can we construct from that, let's say, the energy momentum tensor? And it turns out that in a CFT, there's a transformation which is called the saddle transform, which allows you to take operators with dimension delta and spin j, two operators with dimension 2 minus delta, and the spin is flipped. And this resonates very nicely. This actually saddle transform has been used in partial wave expansion of conformal field theory amplitudes in general, not just 2 dimensions. But in our case, it is a map. It is a transformation that allows us to map states with these conformal weights and spins to those. And this basically tells you that you can take a soft graviton with dimension 0 and convert it to an operator with dimension 2 and spin 2, which is what we would expect for the stress energy tensor, the energy momentum tensor. And indeed, it turns out that if you go to the Mellin amplitudes, you look at the conformal soft limit, delta goes to 0, you take the Mellin transform, you find that in a Mellin amplitude that involves conformal primaries, you find this exactly expression, which is nothing else but the word identity of conformal symmetries. It actually, moreover, implies that the OP of this stress energy tensor, energy momentum tensor, with approach to primary, takes this form. You see that we have singularities when the position here of this operator approaches the position of the conformal primary. And this thing implies that these conformal primaries, which in our case are gauge boson or graviton celestial CFT operators, are actually Virasoro primaries. So it kind of hints that there is a bigger symmetry, not just global one. Now we would like to get also the algebra. And in order to get the algebra of these conformal transformations, Virasoro transformations, we would like to get the OP between 2 energy momentum tensors. And in order to do that, we take double soft limits, conformal soft limits of our correlators. And when the position of one energy momentum tensor approaches another, we find very nicely an expression like that, which is nothing else. It doesn't imply nothing else that the OP between 2 energy momentum tensors is given by this expression. This is exactly what you expect in a 2-dimensional conformal field theory. But actually, we find here that there's no quartic term that would correspond to a conformal anomaly. Of course, we have been working with 3-level amplitudes, so who knows, maybe when we consider loops, we will find some conformal anomaly, but we don't know. You can do the same thing for gravitons of opposite helicity. You can find that the OPs are regular. At the end of the day, in passing, I would like to say that also we can consider conformal soft gravitons with dimension 1. And these are these operators here. And if you take an antiholomorphic derivative of those, from these primaries, you construct a descendant that has very nice, it has some quite intriguing action on conformal primaries, which looks like that. It looks like a current, like a conserved current of the 2-dimensional CFT, but what it does in addition is that it shifts the dimension by +1. And I already said that translations acting on amplitudes, they tend to shift the dimension by +1. So it kind of tells you that this field should be associated with super translations. You can check the conformal properties of this operator and find that indeed it is a primary from the holomorphic side, but it transforms as a descendant from the antiholomorphic side, as a level 1 descendant, as we say. Okay, so everything is consistent. You can find also that these two P's, let's say they give you a regular OP, therefore, in a sense, we say they commute. Now we come to the symmetry. We know that we have the OPs of the energy momentum tensor. We can expand the energy momentum tensor in terms of Virasoro generators. We can do a mode expansion, and we will get nothing else but the standard Virasoro algebra. But we would like to see, we can see something more. There's another symmetry there. And it turns out that we can construct generators of this form. We can construct operators of this form, which are given by commuting basically the energy momentum tensor with this specific operator that's responsible for shifting the dimensions of conformal primaries. And it turns out that if we commute this operator with any conformal primary, it results into a shift of the dimension of the conformal primary. It shifts by 1/2 the holomorphic, by 1/2 the anti-holomorphic. Therefore, dimension shifts by 1, but spin does not change. But now we find that we have in front this ZZ bar dependence, which is telling you that this should be associated with super translations, because basically the shift on these operators is dependent on the direction of the celestial sphere, on the point of the celestial sphere. So it's what we would like to, what it seems that this corresponds to the super translation generators. So now we see that in addition to the standard translations, we have super translations, and we can check the algebra of all these guys, and we find very nicely that super translations commute. On the other hand, we can find that the Virasoro generators with super translations produce this algebra, which turns out to be the BMS algebra that has been proposed some time ago by Bondiberg, Mercer, and Sachs, and by Barnett-Troshire. But we find no central charge extension, which was proposed. It's something that could be in this algebra by a work of Barnett back in 2017. We just find these terms here. We have no central charge terms. And this is basically what we call extended BMS algebra. It has super translations and super rotations. So now we have basically shown that conformal soft theorems lead into word identities, and word identities lead into an extended BMS algebra, which was our target. What we want to do now is to extend all this discussion to supersymmetry. So the first thing we would like to do is to construct supermultiplets of conformal primary wave functions. We start with a chiral multiplet. It's composed of a scalar conformal primary wave function, which we already discussed, is a Mel transform of plane waves, and a fermionic conformal primary wave function, which is a Weyl spinor, which is basically solves the Weyl equation. And you can see that comes from a Mel transform of the standard spinors of momentum basis. This Weyl spinors of the momentum basis, and it's something that has actually dimension, again, delta. You can see here the conformal weights, holomorphic and anti-holomorphic, but it has a spin 1/2. And we can check that this is orthonormal. Supersymmetry now. What we would like to do is to show that we can relate via supersymmetry the bosonic ones to the fermionic ones. In order to do that, we take our quantum field phi and we expand it not in a plane wave basis, but in a conformal primary wave basis. Here, this minuses, they mean ingoing or outgoing, actually, scalars. I'm not going to be using this. I'm going to kind of suppress them here. They imply, this plus implies an ingoing and this minus an outgoing. So when we expand this field in terms of conformal primary wave functions, we find oscillators A and A dagger, or the same thing for the fermions, B and B dagger, which what they do basically is to create or annihilate states with specific conformal dimension under the global SL2C on the celestial sphere. So they basically create or annihilate specific wave packets. They create specific states that have nice conformal properties. And you can easily check that these oscillators that are right here are nothing else but Mel transform of the standard oscillators in momentum basis. And you can easily deduce also their algebra, a commuting algebra, this type of algebra for the bosonic and this for the fermionic. It's a standard algebra. Having done this thing now, we can see how supersymmetry can work. We know that on-cell supersymmetry transformations, they take a scalar into a fermion. This is the supersymmetry parameter eta here, and these are the supercharges, Q and Q bar. Okay. So we can apply the expansion that we did before, and we find that very simply supersymmetry takes oscillators, bosonic oscillators, into fermionic oscillators, or fermionic to bosonic. Okay. So this whole thing depends, of course, on the supersymmetry parameter and this vector Q that parameterizes it's the spin or helicity notation for the vector Q that we've been using all along. So, moreover, it shifts the dimension by +1/2, as we can see. So now comes the how do we relate this to celestial CFT? Holography tells us that we should associate an oscillator that creates or annihilates a specific state on the celestial sphere, on the asymptotic boundary, of the four-dimensional space-time, with specific operators on the celestial sphere. So we associate these oscillators to operators, fermionic to fermionic operator. And then if you continue this story here, this implies that we know how to make a supersymmetric transformation of an operator on the celestial sphere. And it turns out that here, for notation, to make notation easier, I have separated my operators, the operator content, into two sets depending on the spin. This set has spin, we call it spin J, and this J complement. You can see that, for example, the carrier multiple is supposed to have a complex scalar with spin 0, and a Weyl fermion with helicity with spin +1/2 or -1/2. The important thing, just to say this thing, in order to be able to just make things easier to follow, is that supersymmetry takes a state from one set of spins to another set of spins. And in actual terms, it converts a bosonic one to a fermionic, or a fermionic to bosonic. So it's kind of a condensed notation that takes into account the full multiplex content here. So we have found how supersymmetry acts on celestial CFT operators. Okay, we can repeat the same thing about the OPs of fermionic fields.
We have 10 minutes left.
Yes, thank you. So we can continue with OPs of fermionic fields. We can do the same thing that we did before for bosonic ones. We find that same helicity, gauginos or gravitinos have no collinear singularities. And opposite helicity, though, fuse to gluons of gravitons. And once we take the Mellin transform, we can show that one gravitino operator with spin -3/2 and one with +3/2 can fuse to give you a graviton with +2 helicity, +2 spin or -2 spin, with this typical, as I explained before, singularities, Z over Z bar or Z bar over Z. And the coefficients here are beta functions, which you can already see, these beta functions. They show that if we take a one conformal dimension to approach 1/2, then they blow up. And this is a signal of a conformal soft theorem. We said that we expect that we're going to have some conformal soft theorems where the Mellin transform blows up when dimensions of some operators take spatial values. And here we can see it already from this story here. Okay, so what can we do now to find the symmetries? We're going to go to the soft fermionic theorems, very similar to the bosonic ones. We can we can consider an n+1 point function that involves gravitinos and gravitons. And then you can check, it has been done by several authors in the past, that the leading singularity, soft singularity under one gravitino, let's say becoming soft, goes as 1 over omega s to the 1/2, while there is a subleading term which goes this way. These operators here, these factors here, they're universal again. This is a universal factor, this is a universal factor. They have the same structure, no matter what is the field content of the amplitudes. They are moreover though operators because they need to act on the remaining amplitude that involves the hard states and convert a boson to a fermion or a fermion to boson. This is required by spin statistics because if the original amplitude has an even number of fermions, when we factor one gravitino, at the end of the day, the spin of one other state in the remaining amplitude needs to change in order to have an even number of fermions. So these are operators here, they're not just expressions of momentum polarization. You continue the same story, you do the Mellin transform of amplitudes like that, and you look at specific limits of the conformal dimensions. And indeed, it turns out that if you take a gravitino correlator with various states in this first set J and other ones in the set JC, so these are all conformal primaries that belong in the one set of spins or the other set of spins, you find a divergence when the dimension approaches 1/2. And this is nothing else but a conformal soft theorem for fermionic operator. So, okay, that's quite interesting. And we would like to see what is the word identity associated with that. What are the symmetries that basically stem out from that? In order to do this thing, we will follow the same idea that we followed before. We have a conformal soft operator that has dimension 1/2 and spin minus 3/2, but using a shadow transform, I can convert it to a supercurrent that has conformal dimension 3/2 and spin 3/2. So it's a purely holomorphic one. Or I can take the opposite spin conformally soft operator, do a shadow transform, and I'm going to get eventually an anti-holomorphic supercurrent. The interesting thing about these guys, which are called supercurrents, is that when you apply them on conformal primaries, you get very nicely poles that you would expect exactly from a supercurrent and a shift in the dimension. Moreover, they change the spin statistics from, let's say, boson to fermion or from fermion to boson. You remember when I change spin from this set to this set, this implies that I change statistics. Okay, you can do the same thing for these guys here. You can also construct charges from them, okay? And if you want to discuss the globally well-defined charges, you end up with this type of identity. So you construct a charge like this one by using a superconformal, a fermionic parameter like this one, which has to be up to linear order in order for this charge to be to fall off. I'm sorry, in order for the integrand here to fall off nicely at infinity. And in order, therefore, for this is standard CFT again construction where you construct a contour integral of these guys here, and you construct the charge. And if you want to consider global transformations, this must be well defined at infinity. You insert it in a correlator of conformal primary operators, and very nicely turns out that these lead into these word identities, which are nothing else but the celestial CFT realization of the four-dimensional SUSY word identities. So they relate correlators with different content, different correlators between each other. They are the identities that, of course, you can see if you go up into the four-dimensional picture in momentum basis. But here they are in this picture of the celestial CFT. So having done this thing now, we would like to understand the algebra of these operators. And again, what we do is to take double soft limits of correlators. And from that, we should extract the algebra. So what we do, we can take the double soft limit of a graviton and a gravitino, take the shadow transforms, and we find indeed that this supercurrent transforms as a spin 3/2 primary. And the same thing for the S bar. Moreover, we find that these supercurrents commute with the P operators that are associated with supertranslations. Interestingly, the two same holomorphic, let's say, supercurrents, they also have a regular OP, which means that they commute. That we'll see it's relevant to supersymmetry. What is, though, very interesting is that if we take a supercurrent of one spin and this, the holomorphic and the anti-holomorphic, I can construct a composite operator whose action on conformal primaries has this form. It shifts the dimensions, and it has a holomorphic and anti-holomorphic pole. This actually is a dimension 3 scalar. And some time ago by Barney, a similar operator was constructed basically by taking a formal Lorentz series of the supertranslation generators of the BMS algebra and constructed a field like that that has this action on primaries. We find it here as a composite operator between two supercurrents. And from the point of view of the four-dimensional theory, is a two-particle state. So it's something completely novel, which we've never seen before. Could be interesting too. So in order to complete our algebra, the only thing that is missing is to construct, basically not to construct the algebra, we need to expand the supercurrents into generators. We do a mode expansion. So these are the generators. We take the supercurrent, we expand it in terms of generators of this type here, and we can check that these generators acting on conformal primary wave function, conformal primary fields, they have the expected behavior of shifting spins by 1/2, changing the statistics, and of course, they have some term that depends here on the coordinates of the celestial sphere. The zero modes of these guys here actually are nothing else but the supersymmetry generators I discussed earlier, starting from the conformal primary wave function. So the zero modes are exactly supersymmetries. But now we have more generators. We don't have just the zero modes, we have more. We have found that these supercurrents include an infinite number of them. The last step, and basically this allows us to construct the algebra completely, is to take an anticommutator of 1G and G bar. And it turns out that if you do this thing and you act on a conformal primary, you find an action like that. This action is exactly the action of super translations on conformal primaries. They shift the dimension by +1, and they have this angle dependent, I say angle dependent because it depends on Z and Z bar, term on the celestial sphere. In total, the algebra that we find is the Virasoro algebra, which I have not written here, and the extended BMS algebra that I wrote actually earlier, which includes all the Virasoro and super translations, and in addition, this type of algebra. This part of the algebra is what you would expect from a two-dimensional superconformal field theory. But you don't have a superconformal field theory for the very simple reason that G and G here commute, anti-commute actually. Normally, these two guys, if we had a superconformal symmetry, should close on the Virasoro generators. On the other hand, here, they give 0. But the novel thing is that now G and G bar, they anti-commute on the supertranslation generators. So we cannot say that we have a two-dimensional superconformal theory, but we have actually some extended BMS, which we call it with fermionic symmetries, which we call it super-BMS algebra. So in conclusion, and I finish here, we have found an infinite dimensional algebra of which we call it n=1 extended super-BMS. A similar construction has appeared recently, just last week. I didn't have a chance to read the whole paper, but it's quite interesting by Mark and collaborators. And they also find an infinite number of fermionic charges, just like we have. Originally, this had appeared as a construction back by Awada, Gibbons, and so, but there they had considered, if I remember correctly, only the global charges. Here we find an infinite number of supersymmetries, I will call them. Just like we say super translations, these are supersymmetries. Similar algebras also have appeared in 3 dimensions, which maybe the story there is a bit more clear. But what I want to stress is that we never find a world C 2-dimensional SUSY. That means we cannot say that we have a superconformal symmetry on the celestial sphere. Maybe it is realized on the spatial limit of the celestial CFT. Maybe we can find a similar limit as done in 3 dimensions in these realizations here that I don't discuss, that we can recover somehow a world C 2-dimensional SUSY. And with this one, I'm going to close my talk. The other things that I would like to study in this picture will be actually particularly the conformal bootstrap, which I'm not going to say much here because I run out of time, but there are many things to do beyond supersymmetry. Okay, and that's it. Thank you.
Okay, thank you very much. So we have time for some questions, and I see that Gaston wants to ask. Okay, start, Gaston.
Yeah, should I stop sharing just to...
Well, maybe the questions will refer to
okay, perfect.
Yes, so maybe you keep the slides, okay. I guess. It could
perfect.
be.
Yes, yes. Yeah.
So Gaston, go on.
Thank you. Just wondering about the superconformal algebra, actually. You say, just to understand, you have this G and G bar, right? So, but this is an n=1 superconformal algebra. So
it should have been an n1,1 because I have
okay.
G and Z bar.
Okay,
but I don't get
that's my. So it's 1,1. So usually in the standard superconformal algebra in N=2 in 2 dimensions, you have this J current, which is like a kind of R symmetry or something like that. You have an additional U current. So what would play the role of this J here?
Oh, sorry, it just it took me out of the
I like the outline anyway.
Yeah, thank you. Sorry about that. I would like to go back. Okay, so as I said here, we do not find a superconformal symmetry. If we had a superconformal symmetry in the 2 dimensions, we should expect this G and G, the holomorphic currents, to close on the holomorphic Virasoro generators. Okay, and then of course I could also go and ask, well, can I have an n=2, right? But here we don't find this thing. You see, these guys here, the anti-commute. If you go to string theory, for example, as an example, you will see that these generators here, they close on the Virasoro generators. Here, the anti-commute, they don't close. It seems that we don't have factorization. If you were thinking of it as superconformal algebra, we have G and G bar that basically the one's holomorphic and the other anti-holomorphic, and they do not anti-commute. So I'm not sure if I answered your question, but I don't see how we can realize an n=2 here if already we don't have an n=1.
Okay.
Does this answer your question, or you were saying something?
Yeah, no, yes, I was wondering whether since you have a 1,1, whether it was a clear way
we were hoping to have 1,1.
Getting the n=2, but this would, in addition to ask for this R symmetry operator.
Right. The hope would be that maybe in a special limit, you would be able to recover some superconformal symmetry. And what I'm referring to is that I know that from work of Glenn, that you can take some kind of Inor-Wigner contraction of some 3-dimensional spacetimes, and then you get some kind of superconformal symmetry. But I don't know how to do that in 4 dimensions. Okay, so maybe there's some kind of limit.
Okay, next question, Kostas. Okay, sorry, Konstantinos.
Hi.
Yeah. Hi.
Can you hear me now? I have a very simple question on page 13.
Yes.
This expansion for small omegas.
Right.
And you mentioned that at least 3 terms are universal. Is that correct?
That's correct. 3, only 3 are.
So that, okay. So the 4th one is not.
No, so yes, the 4th one is not. So exactly, after you go beyond this order here,
yes, okay,
the terms are not universal. No, the same thing for gauge theory. Yeah, that's not
on the previous slide, page 11, actually.
Mm-hmm.
You mentioned something on beta functions. You don't really mean of running couplings of something. You mean
no.
Okay.
Other beta functions, the Euler beta functions.
Okay, thank you.
Yes,
thank you.
Yeah.
Okay, we have also a question by Andrea.
Mm-hmm.
Please go ahead.
Yeah, I was wondering if you could sort of go back, well, start with the superconformal algebra and then try to engineer what you would have to add. Because now we know a little bit about how things work, momentum shifting, dimension shifting operators, and so on. Do you think one could work backwards?
Yeah, you mean to start from the celestial CFT algebra and go backwards? Is that what you're...
Yeah. I mean, you're taking a limit in going there because you're taking the collinear limit and so on. So it would be maybe hard to undo that. But I don't know, maybe one can learn something.
You mean, just a second. Okay. So you mean to go backwards in this picture? If you know the OPE, how to go back to the collinear limits? Is that what you have in mind?
Yeah, if you start with a superconformal algebra and then ask, okay, what do you need in order to arrive at that algebra? Yeah,
okay. As I said, in the bosonic case, just to go a bit ahead on my slides, this was a very interesting work done by these authors here, and they did exactly this thing. They started assuming that we have this thing here, this expansion, but you don't know these constants. And they applied BMS symmetry and some Kac-Moody symmetry that exists when you have gluons. And they were able to determine this thing here. So now if you know that this is an Euler beta function, you can probably run backwards, I'm guessing, and figure out what is the energy I'm sorry, what these collinear singularities look like. I kind of took these things out to find exactly what are the collinear singularities.
Yeah, I mean, you would have to undo an integral and the limits, so it might be difficult to know what one had to start with. But
well, if you are taking the limit of the conformal dimensions, I agree. I'm not so sure how to do that, but I think if you look at it, again, and to go to this slide right here. Oh, this thing is not helping really. 1 second. Yeah, I need to go to the specific part of the. Yeah, I think I took out this guy here. So basically, the way these authors worked this problem was by saying, okay, if I know I have Einstein-Yang-Mills, I expect this type of singularities just by dimensional reasons. Okay, so I would say that I'm not sure if you would be able to undo completely the fact that here this thing depends on conformal dimensions and go backwards and find the energy dependence. But I would guess that it's probably possible. And actually, maybe that would be the interesting thing. I should say that how can you start completely from first principles, okay, on the celestial CFT and do the same thing for the supersymmetric case, like you asked, and try to go backwards and see if this predicts what is the behavior of amplitudes in collinears and soft limits, possibly, of the gauge theory or gravity theory. So again, I haven't thought how to do it exactly, but I guess it should be possible because exactly what this guy succeeded here. But yeah, it's not 100% obvious. Yeah.
Okay, I do not see any other questions. So let's thank our speaker again.
Thank you very much.
And
I'm going to stop sharing, yes.
We have a break until 3:45.
Okay, perfect.
So thank you again and see you
Thank
then
you very
in
much.
10 minutes.
Of course.
Bye-bye. Infinity. So you can start.
Hello, everyone. First of all, I'd like to thank the organizers for giving me the opportunity to present my work here. So this is work done in collaboration with Mark Heno and Javier Matulich. These are the table of contents. Now, the remarkable feature of gravity is the enhancement of asymptotic symmetries over background isometries. And these are the seminal examples. In this talk, we are going to deal with asymptotically flat space, whose asymptotic symmetry group is the BMS group. It is also infinite dimensional. Now, initially, there was some skepticism. So first of all, the infinite enhancement. Is it a gift in the sense that it would enrich physics? But then how are we supposed to interpret so many symmetries? What are their physical interpretations? Also, there was initially some incompatibility between studies at spatial infinity and null-infinity, because while the BMS group naturally emerged at null-infinity by their analysis, similar studies at spatial infinity could not reproduce the BMS group. So there are questions like whether BMS group is intrinsically connected to gravitation and radiation, so null-infinity is the natural background. But nowadays we understand these problems better. So first of all, with the soft graviton theorems, now we know that we can relate this to the extra charges through word identities. So the BMS symmetry is a true physical symmetry of the theory. Now, if something is a true symmetry, it should be visible in any formulation. So we should expect to recover it at spatial infinity as well. And indeed, this was achieved by Mark and Cedric, where by some modification of the conventional boundary conditions, they could indeed recover the BMS group at spatial infinity. And this was a very important progress because it then disentangles the existence of BMS symmetry from the intricate dynamical questions about null-infinity, existence of null-infinity, smoothness properties, etc. Now, what about supersymmetric extensions? For supergravity in 4 dimensions, a graded extension of the BMS algebra was exhibited to be a symmetry of the theory. This was achieved by Awada Gibbons-Shaw. This analysis was also carried out at null-infinity. Now, one important feature of this algebra, I think this was mentioned in the last talk, is that the algebra contains only 4 real fermionic generators. So out of the infinite number of angle-dependent supertranslations, which are characteristic of the BMS group, only the ordinary angle-independent translations have a fermionic square root. So as I mentioned, this analysis was carried out at null-infinity. Can we reproduce this algebra as spatial infinity? This is the topic of my talk today. So for this, we start with the action of n equal to 1 supergravity in 4 dimensions expressed in canonical form. And we choose the time gauge. Here, the lower index is the spacetime index and the upper one is the local Lorentz index. And so these are our dynamical variables. The third line expresses the constants with the Lagrange multipliers, and then we also have a surface term, which I will return to later. And the constants are all first class and are related to the gauge symmetries of the theory. So these are the forms of the constants, the Hamiltonian and momentum constants, the fermionic constants, and JAB, they generate local spatial rotations. Recall that we have fixed the time base, so now the only freedom we have are SO3 transformations. Now see that there are some F terms which are actually fermionic terms here, but I have not written down their explicit expressions because they are not needed here. The reason I will explain to later, but you can look at these references for their explicit forms. So now we go to boundary conditions. We have both graviton and gravitino. First, let us consider graviton. So since we are dealing with asymptotically flat spacetimes, we take the spatial metric as the perturbation over the flat space metric. And we asymptotically freeze the freedom of performing arbitrary spatial rotations of the triads by imposing this gauge condition. Now, since we have fermions in our system, it's natural to work with the Fierwin coordinates because they couple naturally to the fermions. But note that by fixing this gauge, the local frames have been tied to the metric asymptotically. So the boundary conditions on these Fierwin coordinates are completely specified by the boundary conditions of on the metric variables. But this is exactly what was achieved by Mark and Cedric in their work on pure graviton. We'll work with the boundary conditions. And in fact, this was reviewed yesterday by Sucheta and Javier, so I will just briefly discuss them without going into the details. So first of all, for the spatial metric, we take the fall off as 1 by r, and its coefficient h bar ij we decompose into even and odd parts. While the even part is arbitrary, the odd part is fixed to be given by an improper gauge transformation. And note that this is in contrast to the strict parity conditions by Reje-Teitelbaum, where they took the odd part to be strictly 0. Here we are allowing a non-zero odd part, so it's called the twisted parity conditions. And similarly for the conjugate momentum, its fall off is now as 1 by r squared. Again, it has odd and even parts. Now the odd part is unrestricted, but the even part is restricted to take this form. And again, this is the twisted parity conditions compared to the Reje-Teitelbaum condition. Now, in addition to these conditions, it turns out that there is another technical requirement. The mixed radial angular component of the metric, if you naively apply these boundary conditions, it turns out to be of order 1, but by hand, we put it to be 1 order higher. We impose that it goes as order 1 by r. This is related to the finiteness of the symplectic form, boost, etc. So after imposing all these technical conditions, they showed that it leads nicely to the emergence of the BMS group at spatial infinity. So this is all about graviton. Now let us turn to gravitino. So we have to devise suitable boundary conditions on the gravitino, demanding that they should make the action finite, they should be invariant under global supersymmetry characterized by a supersymmetry parameter epsilon that goes to a constant spinor at infinity, and they should make the surface integrals appearing in the supersymmetry generators finite. So we took the fall off as fermion as 1 by r squared with a coefficient chi, which is a function of the angles. Now, a slight digression, you may ask if these are the optimal fall-off conditions, or is there a possibility to relax these fall-off conditions consistently to get some more interesting physics. This was in fact our next project, and this will be covered by Oscar in the next talk. So anyway, returning to our 1 by r square fall-off, first of all, we can immediately see that the kinetic term is finite using this fall-off because the kinetic term is quadratic in fermions. So the integrand goes as 1 by r to the power 4 and the volume element is dr r squared. So this boundary condition makes the kinetic term finite without the need to impose any extra parity requirement. So this is already an important result because for the spin 1 and spin 2 cases, we have seen that in addition to the fall-off conditions, we also need some extra parity conditions. But here we see that even without parity, the kinetic term is already finite. Now we have to check the supersymmetry transformations. To leading order, the supersymmetry transformations acting on the canonical variables are given by this. And we have to show that the supersymmetry transformations with this fermionic falloff respects the boundary conditions of all the fields. Now we take the fermionic parameter to be order 1 at leading order. Now recall that Hij and Πij, they have some parity requirements at the leading order. But here we see that with this falloff, under supersymmetry transformations, they are disturbed only at subleading order. And there are no parity requirements on the subleading order. So the supersymmetry transformations on H and Pi are consistent with this falloff. Now for psi, recall that the falloff was psi as 1 by r square, but there was no parity requirement. The second and third terms are fine. They changed psi to order 1 by r square. But when you see the first term, now you see that merely being, the leading order of epsilon, merely being order 1 is not sufficient. Because even if epsilon is independent of r, but depends on the angles, still del I epsilon would be order 1 by r. This is like by chain rule when you go from Cartesian to polar coordinates. So here we actually require the leading order of epsilon to be a pure constant. Not even a function of the angles. So epsilon 0 is a constant spinor, and now we see that the boundary conditions are all preserved under these transformations. Now, finally, the surface integral appearing in the supersymmetry generator can be calculated to this. And then you see that under these requirements, the surface integral is finite and integrable. Finite because this is order 1, psi goes as 1 by r square, and the volume element is r square. And integrable because the leading order of epsilon is constant, so it comes out of the integral. And so this is the expression of B Susi that you get. So now we have seen that with this condition, with this falloff of fermion, it satisfies all the boundary conditions. And so the supersymmetry generator is consequently well defined, and our chosen fermionic falloffs respect all the requirements listed above. There was another technical requirement that was shown by Mark and Cedric. Again, for generic decays, if you naively impose the falloff on the graviton, then the Hamiltonian and momentum constant behave as 1 by r cube in Cartesian coordinates. But again, due to some conditions on finiteness and integrability, we need to impose that they go off as 1 by r to the power 5, that is 2 orders higher. Now, in this case, we have, in addition, some gravitino contributions. If you remember, I talked about some F terms. So now we have fermions in our system, and they also contribute to the Hamiltonian and momentum generators. But due to the falloff that we have imposed on the fermion, those terms fall off even faster, so they do not mess up their result. And they are preserved under the transformations generated by the constants. So these results hold as usual from their old papers. Now we go to asymptotic symmetries. The boundary conditions are invariant under a larger set of transformations than the super Poincare algebra. So first of all, the Lorentz transformations. The invariance of the boundary conditions on the bosonic field was already discussed by Mark and Cedric in their work on pure graviton. Now, since we also have gravitino in the system, there will also be some extra contribution of fermions to the boost variations on the bosonic fields. But again, due to the falloff that we have imposed, those will be subleading and they do not invalidate their result. The graviton result holds as in the old case. And for the fermionic field, delta boost psi goes as chi times del psi, but chi is order r at leading order, and this is 1 by r cube. So again, the whole thing is order 1 by r square, and this is also respected. So we see that these are invariant under Lorentz transformations. And similarly, under translations and BMS super translations also, these can be shown to be invariant. Now, this T and W, in general, they are the angle-dependent super translations, but their zero modes are the pure translations, are the constants, the angle-independent translations. The higher spherical harmonics yield BMS super translations and lead to an infinite dimensional extension of the homogeneous Lorentz group. Again, these points were discussed by Javier and Sujata yesterday. So T and W, the whole of it are not improper gauge transformations. Only the even part of T and the odd part of W define improper gauge transformations. The odd part of T and the even part of W, they do not contribute in the charge. So they define proper gauge transformations that do not change the physical state of the system. And so we can see that the boundary conditions for both the graviton and the gravitino remain invariant under these transformations. And now supersymmetry. The boundary conditions are invariant under supersymmetry transformations that behave asymptotically as this is what I just discussed. The leading order of the supersymmetry transformation is order 1, and not only order 1, it's a constant spinor. There is no angular dependence allowed in epsilon 0, since this would lead to unwanted order 1 by r term in the variation of fermion under supersymmetry. And this is the chain rule that I was talking about. So again, this is an important result of our paper. The global part of supersymmetry transformations involve only 4 independent real fermionic parameters, and it is not infinite dimensional. Again, the question arises, can we get some infinite dimensional fermionic symmetry by some relaxing of boundary conditions? And this will be discussed by Oscar in the next talk. Now, by using the usual Rarita-Schwinger method, we can calculate the surface term. I mean, this is the generator given by combination of the constants plus a surface term, and this surface term is determined by the Rarita-Schwinger method. And in fact, this is equivalent to demanding that the transformations of the fields under super-BMS transformations are canonical transformations, that is, they leave the symplectic form invariant. Now, the surface term accompanying the bosonic transformations was again computed by Mark and Cedric for pure gravity. Now, the inclusion of the fermionic terms in H and Hi, again the F terms, they do not mess up the results due to faster falloff of the gravity. And the boundary term is found to be this. I mean, this is these are all the terms, of which the first 3 are bosonic terms. And again, they have long expressions, and I have not written them down because they are basically the same result as a pure graviton case. And the supersymmetry part is given by this. And note that only the constant part epsilon 0 of supersymmetry parameter appears in the surface integral at infinity. The subleading terms, which would be of order 1 by r, are proper gauge transformations that do not change the physical state of the system. So there are only 4 non-trivial global supersymmetry transformations. Now, the Lagrange multipliers, we take their falloff like this. I'm not going to discuss this. Okay. And finally, we can calculate the asymptotic symmetry algebra. So this is the algebra that we are getting. Now, note that in some important points to discuss about this algebra. So as I said, for T and W, the odd part of T and the even part of W was improper gauge transformation, and the rest was a proper gauge transformation. And the boost parameter is odd. So you can see that the mixing is only between the odd part of T and the even part of W and vice versa. So that is respected. And the bosonic part of the algebra is the same as the pure graviton case. Now our new ingredients are the fermionic terms. So the last line, this is basically the Poisson bracket of boost with the supersymmetry. I mean, this simply expresses that the supercharge is a Lorentz transformation under the corresponding local Lorentz transformations. The important ingredients are these. So the Poisson bracket of 2 supersymmetry, what should it give? And from here we see that the bracket of 2 supersymmetry transformations generically yield non-trivial T's and W's. But from the algebra, you can see that only the 0 mode of the resulting T and the first harmonics of the resulting W are non-zero. So these correspond to ordinary space and time translations. I mean, these T and W are generically angle dependent, but from here we see that only the 0 modes are contributing here. So as I mentioned in the introduction, we recover the square root only of the ordinary translations and not of the generic angle dependent super translations. The anti-commutator of 2 supersymmetry transformations does not yield a non-trivial BMS super translation. And in fact, this is exactly the super-BMS algebra of Awada-Gibbons-Shaw. So we could recover it exactly at spatial infinity. Next, we also considered the case of extended supergravity. So we extended our analysis to the n equal to 2 case. So in this case, in addition to the graviton, there will be 2 gravitini, and also it contains a photon. Now again, the case of photon was reviewed by Javier yesterday. So for the photon, we take the falloff as this, 1 by r falloff for the A field, and again we decompose it into odd and even parts. The even part is unrestricted, but the odd part is given by this. And for the conjugate momentum, we take a fall off as 1 by r squared, and it's purely odd. Now, as we saw yesterday, there are for some properties, for some finiteness, etc. So in addition to these variables, we also need a boundary degree of freedom at infinity that is denoted by capital psi k, which enters the kinetic term of the action through the surface term. And then in this case, you have to show that the photon is consistent with everything. So you have to show that how the photons transform under several transformation laws. And finally, we showed that everything is consistent, and we found this algebra. The important thing is that here also only the zero modes of the infinite dimensional bosonic groups appear in the Poisson bracket of 2 SUSY. So again, here also we got a finite number of fermionic charges. Now these are the conclusions. We have given here precise boundary conditions on the dynamical fields of n equal to 1 supergravity that provide a realization of the super-BMS algebra of Awada-Gibbons-Shaw. It is characterized by a finite number of fermionic generators. We then generalize the analysis to extended supergravity models. No parity condition has been imposed on the spinors. The boundary conditions on the spinors have been shown to be compatible with the twisted parity conditions of gravity coupled to the Maxwell field. This allows us to get the super-BMS algebra. And now the next question arises. So is there a way to relax the gravitino boundary conditions consistently, which results in an infinite dimensional fermionic extension in the Hamiltonian formulation? So this will be covered by Oscar in the next talk. Thank you.
Okay, thank you very much. And thank you for keeping with time. So we have some minutes for questions. So let me, and maybe I can start. And this is motivated by a talk we heard yesterday, the talk by Roberto Tanzi, where he discussed different boundary conditions for the vector field. I mean, opposite parities.
Yes.
Could these be accommodated in this formalism when you discuss extended supergravity? Could you have opposite parity conditions for the vector field?
Yeah, I was also thinking about this yesterday. So I mean, we can try to do this. I mean, here we imposed a particular parity condition, and we needed a degree of freedom at infinity.
Okay, so work to be done.
I mean, we can think of that. I don't know the answer.
Okay. I do not see any other question. Ah, no, there is one by Susheta. So Susheta, you can unmute yourself and ask your question, please.
Yeah, it's also not really a question, more of a speculation. If we do try to impose opposite parity conditions on the vector field, do we not lose the U1, infinite dimensional U1 for the vector fields?
Yes, there is a risk.
I was just,
we have to check.
because for Yang-Mills, as we saw yesterday, it was not possible to get an infinite dimensional extension with the opposite parity conditions. Although the reasoning was different there, but anyway, I was just wondering.
Yeah, but I think the nonlinear terms were the
nonlinear terms were the problem. But at the end of the day, the parity conditions for pi I were not really compatible with having infinite dimensional U1. But I was just thinking.
Okay, Yannick has a question, so please ask your question.
Yes, I was wondering, so in the extended case, in the n equal 2 case, is there a sense in which you see the super-Poincare group sitting in the super-BMS group? How does that work? Because there was this discussion in the previous talk that they were wondering whether or not you could extend the super-BMS for n equal 2, but here it seems that that's really what's going on, that the super-Poincare group gets embedded into this super-BMS.
Yes, but only with a finite number of fermionic generators. Yeah. It's still finite.
Yeah.
It's doubled, or but still finite. But you do have a super Poincaré, yes.
Yeah, I mean, this is the.
So I mean, so it means that in some sense this n equal 2 super Poincaré sits inside for both n equal 2. I mean, am I right to think that both n equal 1 and n equal 2 sits inside this super BMS group?
Yeah, I mean, that was one of the requirements. You have to check the compatibility.
Right, okay, thank you.
But you have an n equal 2 super BMS and an n equal 1 super BMS. I mean, the number of fermionic generators is not the same, I guess.
Yeah, I mean, here we got 8.
Okay. Any other question? Well, if not, let's thank Turmoli again. And we can move on to the next speaker, Oscar, about the asymptotic structure of the Rarita-Schwinger theory in 4 dimensions at spatial infinity. So Oscar, you can take over.
Yes.
So you are here. Yes.
Hey, yes, I'm here. Okay. So
you can.
Yes, let me move because I have a mess with my windows. Here, okay. So I have to put share.
Share screen, yes.
Share screen. I want to share this one. And I think this is the talk. Yes. Okay, so I'm gonna put the full screen.
Full screen will be better. Yeah.
Yeah.
Okay, good. So
okay.
You can start. So it's 25 minutes plus 5 for questions.
Okay, okay. So thank you, the organizer, for giving the opportunity of presenting our work in this very nice workshop. This is a work in collaboration with Mark, with Sucheta, Javier, and Turmoli. And we work the asymptotic structure of the Rarita-Schwinger theory in 4 dimensions at the spatial infinity. This is a work based on this paper that we recently put on archive. Okay. Okay, so so first, a very brief introduction. I think that Turmoli already talked about BMS, but I'm gonna say this, that the analysis of the asymptotic structure of gravity has taught us that the algebra of the asymptotic symmetry can be much larger than the algebra of the background isometries. This is the case of BMS, obviously, in general relativity, but for asymptotically flat spacetimes, and for asymptotical ADS spacetimes in 3 dimensions, where Brown and Henault showed that the boundary conditions in that case were preserved by the conformal group, and whose canonical realization is centrally extended, given the 2 copies of the Virasoro algebra. So these results have been widely extended in many directions, and we have found, I mean, in the literature, there are a lot of generalizations and extensions. In particular, we have the graded extension of the BMS algebra found at null-infinity by Awada, Gibbs, and Shaw in the 80s, 86 years. And recently it was found at the spatial infinity by Mark, Javier, and Turmoli. But the thing with this algebra is that only has a finite number of fermionic generators. So we have an absence of square root for translations. But however, there are group theoretical arguments that were given in the paper of Awada, Gibbs, and Shaw that indicate that the extension of the BMS algebra, that it should exist some extension of the BMS algebra with an infinite number of fermionic generators. This sort of extensions have been found at null infinity in these papers, and was explained by Angelos in the last talk. I mean the talk before Turmoli. But one question that arises is that if one can develop a consistent Hamiltonian formulation of this infinite dimensional fermionic extension. Well, we have indications in 3 dimensions, where in this paper by Glenn Loga, Javier, and Ricardo, they found a supersymmetric extension for BMS3 as a canonical realization of, in the case of general relativity. for asymptotically flat spacetimes. And also in 4 dimensions, in the case of pure gravity and electromagnetism, Mark and Cedric found the BMS algebra and these angle-dependent U1 transformations at the spatial infinity. So we will start with the simpler free supersymmetric models, because coupling could bring some difficulties, as was shown by Roberto yesterday in the talk about Young Mills. So this is the outline of my talk. First, I'm gonna show you the theory of Rarita-Schwinger and the standard asymptotic conditions that were already shown by Turmoli. Then I'm gonna summarize and I'm gonna show you which are the new asymptotic conditions and some requirements that some good asymptotic conditions could have to satisfy. Then I'm gonna show you the canonical realization of the asymptotic symmetries. And then I'm gonna study the compatibility of the found asymptotic symmetries with super Poincaré and super-BMS, respectively. Okay, so, and then some conclusions. Okay, so this is the action principle in Hamiltonian form for the Rarita-Schwinger theory in 4 dimensions. Here you can find the kinetic term, the Hamiltonian, and the constraint. And we can determine the boundary term, as we know, by asking for the finiteness of the action. And this boundary terms is going to be, I mean, the form of the boundary terms are going to depend of the boundary conditions on the dynamical field. So the follow-up for the standard boundary conditions, as Turmoli show is this one, where psi at infinity goes like 1/r². For this kind of follow-up, the kinetic term is immediately finite, and we can put the boundary term equal to 0. And we can show also the convergence of the Poincaré generators at infinity. And we choose, I mean, in the standard boundary conditions, the Lagrange multiplier is chosen in this way, in such a way that the constraint term in the Hamiltonian action is also finite. So the boundary conditions that I just showed you in the previous slide are invariant under Poincaré, and this is the same with the action, and under gauge transformations of this form, where the parameter asymptotically goes as a constant spinor. So the canonical generator in this form has this way. We can find a bulk term and a surface integral here. On the constraint surface, we can find that the canonical charge vanishes. And this is because we can see here that if we replace the parameter in the transformation law for the spinor, we see that it's not appearing. So the gauge transformations are all proper. But when we put couplings, we turn on couplings, we see that the fermionic constraint acquires nonlinear terms. So this surface integral is not going to be 0. And we get here that this integral is not 0. And the fermionic symmetries are parameterized by eta 0, which has 4 independent symmetries, which are the 4 improper gauge symmetries generated, I mean, that already was shown by Turmoli. So in summary, what do we have? We have that for the standard asymptotic conditions, we have an absence of improper gauge symmetry in the case of the free theory. But what happens if we relax the boundary conditions by putting a 1/r term? Well, we will find some divergences in the symplectic structure and learning generators. But we can cure this by choosing this specific form for the gravitational field, where we introduce something that we call a surface field, and I will explain later why this is. And this is going to be the follow-up for this chi field. And we can see the field mu as all the standard boundary conditions for the gravity. The bar functions are going to be arbitrary angle dependent spinor functions. And okay, now we are relaxing the boundary conditions in this way. That is an improper gauge transformation, and we can see that improper gauge transformations lead to non-vanishing generators. And this is the case, for instance, that of electromagnetism in higher dimensions, where the boundary conditions were formulated in this way by relaxing the boundary conditions by improper gauge transformations. Okay, so one additional requirement that we have to ask on the mu field, that is the field here, is that the constraint has to go faster, 1 over r to the 4. Naturally, it would go as 1 over r to the cube, but now we will ask to go faster. And this is reminiscent to the case of general relativity and electromagnetism in 4 dimensions, as was discussed by Javier and by Cedric in the case of electromagnetism. So this new set of asymptotic conditions is preserved under Poincaré and under gauge transformations of this form, where here now we have this new parameter, epsilon, where now epsilon bar depends on the angles. And now we have bar epsilon that is going to appear in the chart that goes like 1 over r at infinity. And you can see clearly that the asymptotic conditions are preserved by these parameters. So first, one has to show the finiteness of the kinetic term of the symplectic structure under the proposed set of asymptotic conditions. And it is easy to see that at the end of the day, we will obtain this kinetic term for the theory. And now, okay, when one replaces the asymptotic conditions in the kinetic term, one would obtain 3 kinds of terms. One that would throw linear divergences. The other ones is going to be, the other term are going to give logarithmic divergences, and we have a finite term. Okay, so divergent surface terms and total time derivatives and spatial derivatives can be absorbed by a redefinition of B that is arbitrary, so we can choose it as we want. And we have to ask as well, as I told you in the last slide, that the constraint should go faster, like in this way. So the kinetic term will take this form here. And now, after killing all the divergences by choosing B, we have still B prime, and we can choose B prime as in this way, as the same term that we obtain here. And now we have the kinetic term that has this form, and we can put an arbitrary constant here, alpha. When alpha is equal to 2, this means that B prime is 0. So we have that freedom in this case. Okay, so we can show that the action has a true extremum with this new set of boundary conditions, and no, not up to surface terms. The action principle is given by this Lagrangian, where the kinetic term has had this form, remember? Okay, so now we can vary the action with respect to the Lagrange multipliers, and we will obtain the constraints, as we know. And we can vary with respect to the mu field, and we will obtain a bulk term and a surface term. Okay, the bulk term looks like the spatial part of the Rarita-Schwinger equations when we split in space and time the covariant equations. And one can show that asymptotically these equations says us that the higher spherical harmonics of chi bar, that is the limit term of chi, are constant in time. Using that we are on the constraint surface, we can show that this integral is trivially satisfied. And from the field equation of chi bar, we obtain this equation, and we obtain this equation for mu. And we can see that the subleading term in the bulk equation for mu has this form. And using the equation that we obtained for chi, we can see that chi dot, that is 1, that is the subleading term of chi, obeys the Dirac equation on the two sphere. So in summary, we obtain the Rarita-Schwinger equations plus compatible dynamical equations for the leading terms of chi. Okay. So let's analyze now what is called the presymplectic form. So the canonical implementation of Poincaré requires to understand the boson bracket structure of the theory. We can read this presymplectic form from the kinetic term. And we obtain a closed to form, which is degenerate. And this is because exist some vector fields that leave the symplectic form invariant. And the parameters generated the transformations on the fields on these null vectors are given by these expressions here. So the true symplectic form is going to be obtained when one factors out the null leaves of the presymplectic form. And for this, we need some gauge condition that freezes the possibility to move along the null leaves. One could then impose that chi reduces to its first two terms of the fall-off, chi var and chi 1, which have no zero modes because we kill it by this constant here. I forgot to say that this upsilon, the asymptotic behavior of this upsilon, that is a parameter transforming chi, are constant. So we can kill the zero modes of chi var and chi 1, and we can kill the rest of the fall-off, the rest of the subleading terms of chi by fixing the gauge. So in this case, we obtain a true symplectic structure. So now let's see the canonical realization of the symmetries. So we know that omega is invariant under spatial rotations and translations, and these are canonical transformations. However, boost has this problem that the change in the symplectic form under boost is a surface term that is generically different from zero, even in the constraint surface, even if the constraints holds asymptotically. So we have to find a way in order to get an invariant symplectic form. And in this way, one could define properly a canonical generator. One way of doing this is fixing chi equal to 0, but this is the case already explained by Turmoli. But this choice obviously precludes the possibility to obtain infinite dimensionally proper gauge symmetries at the spatial infinity. So we have a solution for this. That is the solution that Mark and Cedric found in 4 dimensions that extend the phase space by adding a new boundary degree of freedom. Contrary of what happens, and Sucheta explained in the case of Pauli fields, where it was not necessary to add a new boundary degree of freedom in order to make the boost canonical. So this case is more similar to electromagnetism in this sense. So let's consider a new boundary field, a vector spinor, rho at infinity, which is extended into the bulk in this way, and whose associated symplectic form is going to be of this form. And we impose that this field transforms in this way. So the change of omega under boost of the symplectic form of associated to rho is going to be of this form. And we can see that this identically cancel the term coming from the whole symplectic form. So the addition of the new field renders all Poincaré transformation canonical. So we can obtain the precise form of the Poincaré generators using this expression here. And okay, you can find the explicit form for in the equations 3.60 in our paper, but I'm not going to put the whole expression because it's too long. So we can now write a new kinetic term with the new field rho, and we can see that the action is going to be invariant under arbitrary time-independent shift of rho of this form. So in summary, we have this set of transformations for the fields, of gauge transformations of the fields, and using this formula related the canonical generators and the symplectic form, we obtain the canonical generators for gauge symmetries. So what we can see here that improper gauge symmetry is threefold. Why? Because we have the epsilon, the parameter epsilon, and the parameter bar epsilon, and the parameter sigma, which is the parameter generated the symmetries associated to rho. And these improper gauge symmetries are labeled by the leading terms of the parameters. So for transformation for which the leading terms are 0 are proper gauge transformations, and we can now force the field entirely to reduce just to its leading term. So this is why we call it a surface field. Another thing that we have to impose is this condition on rho in order to remove the zero modes of epsilon bar from the canonical generator. But this particular choice is very nice because it's consistent with Lorentz invariance and supersymmetry that I will show you next. So the asymptotic symmetry algebra is going to be Poincaré extended with improper fermionic gauge symmetries of this form. This is the algebra, and we can see here that the Poisson bracket between fermionic generators is now going to be centrally extended. So we have a non-trivial central charge. Well, you can see here that by the leading order for the transformation law of the parameters, that the leading terms of the parameters transform in infinite dimensional representations of the Lorentz group because they are arbitrary angles, arbitrary functions on the two sphere. Okay, this is all with respect to the free theory of the spin 3-half field, and now we will show the compatibility of these infinite dimensional asymptotic symmetries with super Poincaré, and for this we choose the simplest case, which is the multiplet 1 and 3-half, and the spin 1 was already shown by Javier and Cedric in their talks. In this case, the symplectic form has this form here, and here we can say a new property that is the analog of our rho field, that is the psi field, that is a scalar field, a boundary scalar field of the theory. One can show that this action, or the action related to this symplectic form, is going to be invariant under rigid supersymmetry transformations up to non-vanishing boundary terms, whose specific form it is put in our paper. But the important thing here is that the change in the symplectic form is a boundary term, but it's not zero. So we know that supersymmetry transformations, all the transformations can be defined up to gauge transformations. In this case, U1 gauge transformations. So in order to obtain a canonical generator or render rigid supersymmetry canonical, we have to add a U1 gauge transformation with a field-dependent parameter of this form. This is going to be the parameter of the U1 transformation. And one can verify that adding this new gauge transformation, the symplectic form is invariant under rigid supersymmetry. This is a property similar to the one shown by Sucheta in the case of boost, in the Pauli-Fierz case. So the canonical generator for rigid supersymmetry is going to take this form, and one can compute the canonical realization of the algebra. That is going to be super Poincaré extended with these new improper gauge symmetries, that these infinite dimensional fermionic gauge symmetries. Here, Gm electromagnetism is the generator of U1 gauge symmetries, generating these gauge transformations, and this is the are the transformation laws for the parameters. Okay, so now we can analyze the compatibility of this new set of transformations with with the super-BMS algebra found by Aguada, Gibbons, and Shaw, and recently found at the spatial infinity by Mark, Javier, and Turmoli. So the simplest case is the multiplet 2 and 3/2, where the spin 2 case was analyzed by Sucheta in her talk. This is the symplectic form associated to the spin 2 field. And again, one can show that the action is invariant, but up to non-vanishing boundary terms. But we can circumvent this problem by performing an additional field-dependent spin 2 gauge transformation of this form, where the gauge transformation is related to the new field chi. I forgot to say that in the U1 case, that the gauge parameter was related indeed with the new field chi in the fall-off of the spin of the fermionic field. And by performing this spin 2 gauge transformation, we can render the symplectic form invariant, and rigid supersymmetry becomes a canonical transformation. So the canonical generator for rigid supersymmetry in this case is going to be given by this expression here. And we can compute the algebra of the canonical generators, that is going to be super-BMS extended with improper fermionic gauge symmetries. Here we obtain again the central extension for the fermionic fields, for the improper canonical generators of improper gauge transformations. And we can point out here that here GTW is the generator of improper bosonic gauge symmetries that is related to the BMS super translations. These are the transformation law for the parameters. Okay, so these are the conclusions of my talk. I think that I'm okay. So we have relaxed the boundary conditions at the spatial infinity, so that the resulting fermionic gauge symmetries form an infinite dimensional algebra, which is threefold because it's parameterized by 3 functions of the angles. We have shown the invariance of the boundary conditions and action principle under Poincaré in such a way that we can define integrable and finite canonical generators. For this, we have introduced boundary degrees of freedom, which modify the symplectic structure by boundary terms. And we also extend the analysis to cover the supersymmetric free spin 1 3/2 and spin 2 3/2 multiplets. In the latter case, we found the consistency, or we proved the consistency of the super-BMS algebra extended by this infinite number of fermionic generators. So questions that would like to address in the future is the relation with null-infinity, because of the interesting results shown by Angelo in his talk about the super extended BMS algebra in the celestial CFT. We want to study the couplings of the theory, in particular the case of supergravity, and how we can relax the boundary conditions that I just present you. We would like to study high spin fermionic generalizations, for instance, in frontal theory, or even in higher dimensions, because the recent results of Andrea and Ankit about the existence of super translations in higher dimensions. So these super translations should have some kind of square roots as well. So thank you.
Okay, thank you. So we have time for questions. So let me see if there are questions. It's the end of the
Can
day.
I ask a question?
Yeah, Ricardo, please. So reactivate your microphone. Yes, please go ahead.
Nice talk, Oscar.
Yeah, thank you.
I'm really puzzled about something, because during the last 3 talks, we have seen 3 different supersymmetric extensions of BMS4.
Yes.
That by Fotopoulos, then Turmoli's one, and yours. And so, could you elaborate a bit about it?
I haven't studied that deep. I don't know if I can elaborate on that because this is something new. We have to study which is the relation between their symmetries and ours. But for instance, one thing that in the case of Angelos, in the Angelos case, yes, is that they have the presence of these super rotation symmetries in the algebra. So we want to try to formulate the theory without super rotations. We want to see if in the case of our directions, we want to go toward towards some super-BMS algebra with infinite fermionic charges, whose are the square roots of super translations, but without the presence of two super rotations. Maybe this is something that we need in order to formulate what we want, as Angelos showed. I don't know. The other thing is that we have threefold symmetries. I mean, we have three independent parameters generating these fermionic transformations. So in principle, I don't know how the symmetries could be related in some sense. Yes, that's what I can say.
Thank you very much, Oscar.
Okay.
Okay, Angelos has a question, so yeah, go ahead.
Yeah, thank you very much for the talk. It's very interesting. The charges that you have found here, if I understand, they're globally well defined, right? The boundary, correct?
Yes.
Yeah. Okay. So in our case, I think maybe there's not really contradiction. What we have found is generators of local symmetry. So what I think is going on is just like Virasoro. You have Virasoro symmetry locally, but when you put it on the sphere, the only symmetries that survive are the global ones.
Yes.
So in our case, also the global symmetries are only the original, I think, supersymmetries of Gibbons and so are good. The other ones are only local, and I would expect if we go on the sphere, you probably lose them, right? But still, they impose identities on the correlators. So I think they're important in the same way that Virasoro imposes symmetries, some kind of relations, the word identities on correlators. And we usually keep them, although we know when we put a theory on a sphere, the only actual symmetries that remain are the global ones.
Okay.
So I think there's no contradiction there, but
yes,
just an idea, yeah.
I agree with you. I agree. Okay, thank you.
Thank you very much.
Okay.
Other questions or comments? I do not see any other questions, so let's thank our speaker again.
Thank you.
And we move on then to the last talk by Yannick on supergeometry of null-infinity and super-twistors.
Okay, so
maybe
I
you
have
should.
I have to stop this.
Yes, you have to stop that and leave. Okay.
Yes, I did.
Thank you. So
okay.
Yannick, you can now take over.
Does that work?
Yeah, it does. We see your screen. So maybe, okay, and it's full screen now. Okay, you can go ahead then. So it's 25 minutes for the talk and 5 minutes for the questions. So go ahead.
So first of all, since I'm the last speaker of this conference, I think it's my duty to thank all the organizers for making this 2 days of conference happening. Because yeah, I think it was very nice. I really enjoyed it, and also considering the situation where we are all locked down in our rooms in our countries, is very good to have all these discussions. So yeah, thank you, thanks a lot, and thank you for giving me the opportunity to present this work. So yeah, I'd like to talk about the supergeometry of null-infinity and coming from ideas from super-twistors. It's based on few works, recent work. So really it's work in progress. And this is motivated by the following natural questions. Is there a sense in which we can characterize the super-BMS group, which we've been discussing in the last talks? Is there a sense in which we can characterize this super-BMS group as being a symmetry group of some super geometrical space, super space generalization of null-infinity? So some sort of super diffeomorphism on null-infinity. It's a very natural question, I think. If yes, then what is the super geometrical structure that you need, which amounts to reducing this super-BMS group to some copy of the super-Poincare group? And then finally, how all of this can relate to the bulk supergeometry. And a closely related question, I think, is how can we construct field theories at null infinities, which are super-BMS invariant in the first place? And I think those questions, they are really intimately related. And it's very natural if you're thinking in terms of the flat holography perspective, you'd like to build up field theories at null infinity, which are super-BMS invariant, sort of in a systematic way. All right, so this is motivation. So really, the actual result I'm going to present, they are about non-supersymmetric case. But sort of really the motivation is that I'm going to try to convince you that this result I'm going to present, they are the best starting point, perhaps, for a systematic investigation of the supergeometrical setting. So this is, the statement is that a lot can be gained. You can answer most of the questions that I asked before in the non-supersymmetric case by using so-called local twistors, or perhaps tractors, depending on sort of things that you like. And this is what I've been working on in these papers. This is based on classical tools from conformal geometry. So local twistors are due to Penrose, but actually it's going back much earlier work from Cartan and Thomas. There was new bits in the literature in the last decades developed by Rod Gover in the conformal geometry context. And really what I'm going to present is generalization of this work to encompass null-infinity. And then really the main point will be to try to convince you that there is a natural, this is all very natural beginning for investigating supersymmetry. Right. Yeah, but so the supersymmetry part is still work in progress, so you'll see that there are bits missing here and there. Right. So first of all, I need to to review for you twistors and their supergeometric extensions, because I should probably not expect that this is usual background. So what I'm going to call here the twistor space of Minkowski space is four-dimensional complex vector space, which I'm going to write like T. It's equipped with an emission metric of signature 2,2. So here's the twistors with Greek letters. And the reason why the twistor space is useful is that you can sort of derive the conformal compactification of Minkowski space from this twistor space. So how do you do that? Well, you consider the space of two planes. So two planes inside this C4, they have to go through the origin, and you want only two planes which are totally null. So compactified Minkowski space are going the set of two twistors, so two guys into C4, which are null, or these two signature metric, and also they have to be orthogonal to each other. Then you quotient by GL2C to actually just consider planes. So it's a very classical construction of conformal compactification of Minkowski space. It's called the Precker embedding, and it's closely related to another realization that perhaps you're more familiar with, which is called Dirac realizations, where you are thinking of conformally compactified Minkowski space as being inside R6 now, but you impose two constraints, or rather you first take the null cone inside this R6, and then you quotient by you look at the projective null cone. So it's sort of more classical. So although the two pictures relate to each other, and the two pictures relate to each other because the point in this R6 is going to be a bitwister, so skew-symmetric twister. So in 4 dimensions, bitwistors, two forms are 6-dimensional, but they are 6-dimensional complex. However, you have a notion of duality on two forms in 4 dimensions. So how duality acts on these bitwistors, and actually it's going to play the role of a reality structure. So now if you look at the subspace of self-dual bivectors, so these self-dual bitwistors, they form a 6-dimensional real vector space. And finally, you have a wedge product on these bitwistors, which gives you a metric, and this metric has actually signature 4,2. So this is this 4,2 from Dirac's realization. Now in Dirac's realization, you look for null vectors, but null vectors for this wedge product are two forms which are simple, and it's known that it implies that two form splits into two directions like this, and indeed it defines the planes. So which is the reason, which is how you sort of relate to this picture. And now self-duality that you imposed as a reality condition now impose that these twistors, they are null and also orthogonal to each other. So this is how you relate the two pictures, but I'm really going to need the twister picture. Right, so then what can you do is that now you have a linear action of SU22 on the twistor space, which induce action on this conformal compactification, which is just the action of the conformal transformations. So in particular, this conformally compactified Minkowski space is an homogeneous space for the conformal group. Good, so this stage is all conformal geometry. So what about Minkowski space and the infinity in this game? So in order to do that, you need to break conformal invariants down to Poincare invariants, and you're going to do that by choosing a so-called infinity twister. So it's a particular choice of a bi-twister which splits like this. So you should probably think of this infinity twister as a point in this R6 that I discussed before. So you pick a point, so an infinity twisters, and it breaks the conformal group down to Poincare. So this Poincare group is the stabilizer of this plane inside the twistor space. And now you have a Poincare group, and this Poincare group acts on these conformal compactifications, but you have different orbits. One of the orbits is just Minkowski space, but then another orbit is the null-infinity. In particular, you see from this realization that null-infinity, in some sense, from precisely this perspective, you can think of it as an homogeneous space for the Poincare group. It's just that you see now the stabilizers are different. So in particular, of course, null-infinity is three-dimensional, so there is one more dimension in the stabilizer. And there is also nice geometrical interpretations in terms of planes intersecting, but it's not very useful probably here. Okay, so the sort of the claim of this talk is that super-twistors have a very natural supersymmetric extensions, and it's a classical result due to Faber from 78 that you can extend twister in a supersymmetric version by just adding fermionic directions. So super-twistor space, I'm going to add n fermionic direction, and together with a bilinear product of signature 2, 2, and n. And here is the super-twistors. I'm going to write super-twister with bold notations. Now, not only that, but you have also an extension of this conformal compactifications that goes through the supersymmetric case. This is a result due to Yuri Manin in 85. He showed that you can define a notion of superconformal super-Minkowski space as space of two planes in this super-twister space. And once again, it's exactly the same construction. So it's space of two planes which are totally null for this supermetric. Yeah, and so what this telling you is that it gives you a linear realization of this superconformal group on the super-twister space, and it induces a transitive action on the superconformal compactifications. And once again, everything goes straightforwardly in the supersymmetric setting. Now you pick a super infinity twister, and it's once again breaks the superconformal group down to the super Poincare group. And once again, you have different orbit of the super Poincare group acting on the superconformal compactification. One orbit is going to be a super Poincare, super Minkowski space. Another orbit is probably what you would like to call super null-infinity. So this is all, of course, local or flat. This is the flat case, and what we really want to do here is look at curved version of that. So how do you construct a curved version of twisters? Well, what you have to do is well, there are different constructions, but the one I want to consider here is making twisters local. So for this, I will need some local twistors mentions on conformal spacetimes. So I need to remind for you that what I'm going to call conformal manifold is a manifold equipped not with a metric, but with an equivalent class of metric, where equivalents are given by rescalings by nowhere vanishing function. Right. So here's one important result. So here this form is due to Penrose, but again, it's much older in spirit. The result is that anytime you have a four-dimensional conformal manifold, you can always construct canonically. There is no choice here. So-called you have a bundle over this manifold, which is the so-called local twister bundle, such that each of the fibers at any points they are just copies of this twister space. So just copies of C4. So how do you work with that? Well, what you do is you pick one representative in this conformal class, and what it gives you, again, it gives you canonical isomorphism of this twistor bundle with pairs of spinors. So this is how you work with local twistors. You pick a representative and you write local twistors as pairs of spinors. And here's the, in terms of the spinors, here's the inner product. And then, of course, you could have chosen another representative. So you have while rescaling, and while rescaling, what this is going to do is act. You're going to have so-called local twistor transformation rules, and they are going just to act linearly. So in this sense, I think that's sort of the message here is that local twistors allows you to work in a manifestly while invariant form way in the following sense, because while rescalings here on the local on this local twistor bundle, they are just linear transformations. So you should really think of this local twistors as some sort of tensor calculus for conformal geometry. Because now all these pairings, they are going to, any pairings that respect the geometry is going to give you manifestly invariant objects, right? So the real reason why this is useful, of course, is not just because you have a bundle, but you have much more. You have so-called normal carton connection, which is a SU22 valued connections acting on this twistor bundle. You can define it in coordinates. So you pick again a metric, it trivializes your bundle, and you sort of define the connections like this. So what is this? Here we have the Zoldering form for this metric, division connection, and the so-called Sharpen tensor. The statement here is that all of this transform in the way it has to transform in order to make sense. Perhaps nice result to Merkulov is that so there are natural equations that you might like to impose on these connections. In particular, if you look at the Yang-Mills equations for these local twistor connections, well, you find out that they are equivalent to conformal gravity. And again, here everything goes straightforwardly in the supergeometric context. So probably the most subtle part is defining superconformal manifold. However, there is this nice work due to Manin, again, who showed that there is a nice notion for any supermanifold of this type. There is a nice notion of superconformal structure, which extends what the usual conformal geometry of the underlying manifold. It's a bit subtle because superconformal structure is not an equivalent class of supermetric on the total space. It's slightly more subtle than this. But for this talk, it's not necessary to understand the details here. It's just that there is a good notion of superconformal geometry. And then Merkulov showed that for n equal 1 and 2, this superconformal manifold, they have a natural local super-twistor bundle. So just, once again, canonical bundle, so that fibers are super-twistors and they split as you expect. You have a normal super-carton connection extending the usual one. And nicely, what sort of the generalization of Yang-Mills equation for this normal super-carton connections, they are just conformal supergravity equations. So everything's, you have a straightforward supersymmetric extensions. Good, so all of this is just conformal. So if we want to do asymptotically flat spacetime, we need to introduce a scale, we need to break conformal invariance. So how do we do this? Well, ultimately, we'll have to introduce some infinity twister doing this job. So yeah, let's come to asymptotically flat spacetime. So before that, let me introduce this perspective, this definition. This is almost tangent spacetimes. Really, it's equivalent to Penrose's asymptotically simple spacetimes. And here is how it goes. So you take a four-dimensional manifold with boundary now, together with, so usually you take a Riemannian metric. Here we want to keep conformal invariance manifest. We are going to take a pair of metric together with a scalar field. This scalar field is either you think of it as a scale or perhaps as a compensator for the invariance, because we want to consider pairs which are equivalent with scaling like this. In particular, it means that so this phi is a compensator. You can always pick the gauge where phi equals 1, and you get a metric. So this object is invariantly defined as a metric. But now you want asymptotically flat manifold. So you want this phi, the scale goes to 0 at the boundary, goes to 0 at null-infinity, which means that this preferred metric is only well defined in the interior because when phi goes to 0, this metric stops making sense. So yeah, it's just rephrasing of Penrose's usual definitions. Why is it useful? Yeah, so just picture, because I think this is the important picture of this talk somehow. So in the interior, you have this pair, and you can pick the gauge phi equal 1, and you have a metric. But however, at the boundary you have phi goes to 0, so now you cannot achieve this gauge phi equal 1, and indeed, as we know, the boundary is just conformal geometry. There is no preferred gauge for the conformal metric. Right. So why is this a useful definition? So here's what Govers highlighted in some of his recent works, is that these asymptotically flat spacetimes are equivalent to the following things. You can pick a conformal manifold with boundary together with the following things, together with the currently constant Twistors. And it should not surprise you because, as I told you before, Twistors really are the object that you would like to break scales. So in a fixed realization, these Twistors you have coordinates, and this phi is precisely the same scale. And now what's very nice is that Einstein's equation now just read as the fact that this Twistor has to be covariantly constant. So it's just, at this stage, it's just a rephrasing of Einstein's equation, but it's very nice. Why is it nice? Because everything here makes sense up to the boundary. There are no divergences, no expansions. You see the conformal connections is just built up from the conformal metric, makes sense. I as well, nothing goes up. All of this is manifestly invariant and smooth everywhere. Crucial point here is that this equation, what this is really telling you, is that it's reducing this conformal connection down to a Poincare valued connection. Okay, so here's the main picture. In the bulk, you have these conformal valued connections, which was these local twistor connections. But now it satisfies Einstein's equation. So, and this equation in this form, they're just telling you that in fact what you have is a Poincare valued connection everywhere. But what's crucial is that it makes sense everywhere, not only in the bulk, but also at the boundary, because none of these fields behave strangely at the boundary. So in the bulk, this is something that you're used to, because you can pick this nice gauge where phi equals 1, and this Poincare connection, of course, is just the Poincare McDowell-Monceray connection that you expect. However, there is something nice happening at the boundary, is that this connection still makes sense. Once again, the only thing which makes the McDowell-Monceray blows up in some sense is the fact that your choice of gauge. This conformal connections itself extends smoothly up to the boundary. So what is this Poincare connections? And this is what I've sort of tried to clarify in my recent work. So let's now work in coordinates for sort of understanding each other. You pick BMS coordinates, so omega u theta, and you open up these connections and you have a look at what this is. So this is boundary Poincare connection. So it's entirely parameterized by two fields. On the one hand, you have this metric on the two sphere, which is there. This is the Levi-Civita connection for this metric. You have also the scalar curvature, but also you have the asymptotic shear. So we've been discussing this a few times during these 2 days. It also enters this connection. So you see it's non-trivial because here it's without derivatives, but in this psi, it enters with derivatives. So the statement is that this Poincare connection at the boundary, here I chose coordinates, but it's an intrinsic description, if you want, of the geometry of null-infinity, including this asymptotic shear. So it's putting the two fields together into a nice geometrical object. In particular, what it means is that the BMS group, which is just a group of diffeomorphism of the boundary, it acts naturally just by a pullback on these fields. So there is sort of the transformation rule for the CAB, for example, for shear is very natural from this perspective. You can have a look at the curvature of this connection, and what you realize is that the curvature is just a function of psi4, psi3, and imaginary part of psi2, which is telling you that really the curvature invariantly encodes the gravitational radiations. So in particular, because what I'm sort of hiding here is that this is really Cartan geometry. So what's happening is that anytime you do not have radiation, so vanishing of curvature, it gives you an immediate reason why it's really telling you that you're picking a Poincare group inside the BMS group, just because this Poincare connection is flat, right? So by itself, I think it's a quite nice realizations. But once again, what I would like to stress is that there must be a supersymmetric extension of that. So again, there is this beautiful result due to Merkulov in '98 that again for n equal 1 and 2, you start with a superconformal supermanifold, and then he proved that existence of solutions to the supergravity equations, they are once again equivalent to just what you expect to having covariantly constant local super-twistors. So it's exactly the same construction as what happened in the non-supersymmetric case. Once again, what this means is that it effectively reduces this connection valued in the super-conformal group. It reduces it to a super connection valued in the super-Poincare group. And just as before, all these fields, they are smooth everywhere. In particular, they should be smooth at null-infinity. So you should get a super-Poincare connection at null-infinity. And the question is, what is this object? What is the super-Poincare connection living at null-infinity? And I don't know. It's clear that it's there, but it's all the details are to be dig up. It's to be done. And so, yeah, so I'm a bit early. So yeah, so what I really try to convince you is that using these local twistors, that's really the right type of object to investigate the geometry of null-infinity in a systematic way and also in a fully covariant form. Here we are, you see, we saw getting rid of divergences, which was of course the starting point of Penrose, but also we are treating violent invariants in a very manifest way. And what you get from that is that it's clear that there is a boundary Poincare connection at null-infinity. And what's more, it has very natural geometrical interpretation. So BMS group acts transitively on this space of Poincare connections, and its curvature invariantly encodes gravitational radiations. So something you might be thinking at this stage is, okay, what about the Chern-Simons theory for this Poincare connection at null-infinity? And actually, it's been worked out very recently by those gentlemen. So you can do this, and indeed, you get what you expect. Yeah, and again, the real point of this talk is that supersymmetric extensions of all of this seems perfectly within reach. There is a solid mathematical foundations for all of this due to Manin, Merkulov. It's also closely related. So this di equals 0 formulation of supergravity equations is closely related to Sukachev and Ogievsky formulation of supergravity. So it's classical work. But here really what we are doing is trying to using this to induce something at the conformal boundary. So of course details are to be worked out, but yeah, so yeah, so I would be really happy to discuss with anyone interested. Thank you.
Okay. Thank you. So we have time for questions. Maybe while people prepare for questions, I have one. So you mentioned that you see super Poincare, but do you have signs of super-BMS? How would you see, and which super-BMS group would you have?
So, okay. So what happens in the non-supersymmetric case is that, so you see these connections, it comes in with a layer of geometry. There is this metric and vector field. And if you just look for the subgroup preserving this geometry, this first layer, you get the super-BMS group. Then if you ask for subgroup preserving this other part, so the full connection, it's sort of, well, generically you cannot do that. But if the curvature is 0, then you get super-Poincare. So what you get Poincare. So what I expect is that exactly the same phenomenon should appear. There should be some layers of geometry inside these super-Poincare connections. And if you ask for just a subset of super diffeomorphism preserving this first layer, you would get something. And probably there's going to be, as we've seen, there is subtlety in, there are different super-BMS, it seems. So probably here there are going to be perhaps 2 layers of geometries. So, and I don't know. And then if you ask for the full connection to be stabilized, you would get super-Poincare.
And how do you determine these layers? How would you, is it related to the structure of the group?
Right, exactly. So, okay. So what I'm hitting here is that this is Cartan geometry. So really the structure group is smaller than the full group. So in this case, the structure group, okay, so what's going on is that really the structure group, which in this case is R times the Poincare group, it's acting on the algebra. What I mean, yeah. So this is the fact that the structure group is much smaller, which is giving you this structure. So I think the super conformal case, the same should happen. The structure group is going to be much smaller, and this is what this geometry is going to tell you what is. Yeah.
Okay, thank you. Any other question? Someone wants to ask a question? No.
Yeah, I have a question.
Okay. Okay, you can
it's
go
a
ahead.
technical question. You went, Yannick, you went very fast on your.
Yeah, I'm sorry.
I understand. In your description of the infinity tensor, the covariant infinity tensor, you had some coefficient mu, rho, phi. What are these? Like,
yeah. Okay,
what are these guys?
Right. So generically, you have few fields, but once you impose Einstein's equations, which are these equations, what's going to happen is that part of these field equations are going to constrain this mu and this rho. So
what are the okay?
So first things, once you
when the mu and the rho, are they? If I go to the Bondi gauge, what are they? Are they?
So okay, they are just going to be derivative of phi. They are going to be like d phi and Laplacian of phi, something like this.
And phi is the scale factor.
Phi is the scale factor. Yeah. So usually you work with phi equal 1. So mu equals 0 and rho equal 0 as well, because they are just derivatives. So you see here, this phi is the scale. So yeah.
So if so if phi equal 1, then okay.
Yeah. Thank you. And so
the next,
again,
sorry, in the connection, I had no time to see what. Can you go back to the definition of the connection? What are the?
So
what are
just
the
one thing. Just one thing I want to say. So again, these field equations, the first one they solve for mu and rho, and then the other ones they are actual Einstein's equations.
Okay. No, when you had this mu connection in the other. In terms of C mu and theta. Or
the Poincaré one.
Okay, so can you just maybe explain a bit more the layer and the components of the connections? What are the meaning there? One is the shear, the C. And
yeah. So can I say this? So here, really, this is going to be a degenerate frame. So it's a one form. I mean, it really depends how you write things. But you can, in some formulation of this component is going to be a degenerate frame. So it's going to be one form on your null-infinity, but with a degenerate directions. So if you want, it's a frame on the two sphere. Yes.
Xi nu A, couldn't that be just the news? Because I see time derivative of CAB. Could it be a way to encode the news, maybe?
So yeah, this guy. U is the U that you expect. So this is the news indeed.
Well, so it should be the news decorated with something, right?
Yes.
Yeah.
But you see here, the point is that the news is sort of organizing this object in such a way that you don't need to pick coordinates. The way transform is just given you by diffeomorphism of this invariant object. But yes, indeed, this is the news. But you see, I'm saying the news transform with Schwarzian derivatives. What I'm telling you is that these connections, when you act with a diffeomorphism on it, you just act with diffeomorphism, you pull back and you act, and you're going to get the Schwarzian derivative for free immediately. And not only this, but you'll get also the transformation rules for the CAB.
Oh no, I agree. It looks like a very nice organization, but we have to digest it. I mean,
that's why the notation. I agree with like your psi is like n and then c. Yeah, digest the components, and psi is a new. And when you say you act with the diffeo, you just take the usual derivative, or there's no covariant rotation.
Well, I mean,
the action of the diffeo on that connection, you mean, is the usual one. It's not the covariantized version of it.
So, I mean, it's really going to depend on exactly what you want to do and what you. So you see, really, these connections, this twistor bundle, it's really something like an extension of the tangent bundle. So just like if you act with diffeos act on the tangent bundle. Here, in the very same situations, the diffeos are going to act on the twistor bundle.
Okay, so you need an extension of diffeo to the twistor bundle, or
exactly.
And there's a canonical one, or
there is a canonical one, yes.
So
just like there's a canonical one on the tangent.
And involve this d mu, the canonical one. Like, do you use in the Cartan magic formula? What is there a Cartan magic formula for the?
Yeah. Well, Essentially, it's just going to be a twist of the linear derivative of each of the coefficients. So yeah, details are not super important here, but yeah, you have a notion of Lie derivative of local twistors, and this is what you would do here.
Okay. Any other question or comment? Well, if not, let's thank our speaker again. Now, this was the last talk, so let me well, thank all the speakers for these 2 intensive, very interesting and instructive days. At least I enjoyed them very much. I guess all of us enjoyed them. So I learned a lot, and it's too bad you could not come to Brussels, but I'm sure there will be other opportunities. At this point, it's standard to say, have a safe trip back home, but since you are already at home, I will just say goodbye and thank you again. So that closes the workshop. So goodbye.
Bye-bye. Thanks a lot.
Bye. Thanks.
Bye.
Thanks.
Bye.